Started, so if you all take your seats, please. And the running order, do we have, we haven't got an agenda printed, have we? But anyway, the running order is first we're going to have the coordinator for the HEATWISE project is going to give a few minutes talking about the project, I guess. And then I'll give a little bit of a talk. And we have Frederick from Luleå Energy, who's going to be talking about the future of district heating. And Mark and I are going to have a bit of a chat about the EU Code of Conduct. Some of you may know what that is. And then we've got a couple of online presentations, haven't we, from Gemma Reeves at Apple Laval and Raoul from Open Compute. They're not physically here, but I guess we will have them online, yeah. And then that will wind up the first session with some questions and answers. I'm sure, hopefully you'll have lots of questions after that session. And then we have a few presentations later on today with a networking lunch. Without further ado, let me hand you over to Attila. So please, Attila, take it away.
Thank you, John. Good morning, everyone. Good morning here in the room, and good morning to everyone online attending this meeting. While we are waiting that I get the presentation on the screen, let me introduce myself and my company. So I'm the coordinator of HEATWISE project, and I'm here for H1 Systems, which is Hungary's leading data center design, build, and operation company. And quick presentation there. And what is HEATWISE about? Yeah, HEATWISE project is a European project which is aiming to integrate thermally buildings and data centers. So what is actually we are doing? We are trying to take the heat that is being produced by the data centers, we try to do something useful with it, and to give it over to the building. So normally what is happening that data centers need cold and the heat is thrown away. This is what we are calling waste heat, while buildings need heat anyhow. So why not to connect the two? So that was the idea. There was a project call, a European call for project that had the intention to solve this problem, no waste. So let's go to the next slide. Just here I wanted to show you how many people are working and how many organizations on this project. So you see it is a quite good coverage of Europe from the north to the south, from Sweden through Poland, Hungary, Romania, Switzerland to Turkey. We've got a fair amount of money, 4.5 million from two sources, European and Swiss sources, and it was 3 years to make this integration. Okay, let's go further. Let's see, click one more. So some of the drivers, so why this call appeared in the work program of the EU. So, and why probably our target groups are interested. Yeah, there are policies, directives, national policies, standards, certifications, which are representing the will of the EU to remove the waste or to turn waste into value. Okay, and probably it is a good cost saving for data centers. So cost saving by using less energy for cooling, which is one of the largest cost factor in the operation next to the IT load, but maybe a new revenue stream for that. So they are not only going to make money out of selling the compute, but also selling heat. And of course, compliance. So everyone is pressurized to do something more in this regard. For the buildings, this is probably cost saving. So probably the heat and the waste is cheaper than a gas-based for various reasons, maybe because of the CO2 tax or just because the price could be better for them. And obviously there's a compliance factor what comes in for buildings. You will see on the next slides. So what are these compliance issues? There is let's start from the top. This is rather an overarching directive. It is just generally saying that let's include on national level more renewables in the energy mix. How you reach it is a national plan. But still, you see that this directive is promoting the waste heat from this. That's no anything mandatory, just promoting, mentioning it. Let's go to the next one, to the build. No. Go back to the so the buildings. One more slide. Okay. No. Go back to the policies. So, that's cool.
Other side. Keep going. That's what that, yeah.
Stop here. Okay, and now we are arriving there where practically where we are building an ecosystem. Yeah, you see between building and the data centers, and which are the policies that are affecting that. So EPBD, yeah, Energy Performance of Buildings Directive, which is implemented in international laws, is saying about new buildings, about renovation. It is giving ratios, yeah, and priorities. For example, priorities for public buildings, yeah, the worst performing public buildings, schools, hospitals, and so on. They have to be renovated. So they are who have to take into account where they take the energies from, whether green sources or carbon-based sources. They have to prepare mandatory energy performance certificates. It is very important for when you want to sell a building. Without this, you cannot sell anymore a building. Yeah? And there is a smart readiness indicator, which is showing about a building how deeply it is controlled by various softwares and softwares that are helping to optimize the operation of the building. Okay. Let's go here. District heating company. So someone has to transfer the heat from one to the other. Yeah, probably it is going to happen by district heating companies. They are obliged to increase the green share of their energy sources in their energy mix, which is obvious. Yeah, it is mentioned also. Maybe waste heat from DCs. And finally, we arrive to the data centers. So what we see here in the energy efficiency directive. There's mandatory reporting about 500 kilowatt size. Maybe it is going to go down. I don't know. We will hear maybe about this. Then labeling is coming up. So there was a project closed last year, led by EY, if I remember well, which was working on bringing in a similar labeling like for the buildings. So already by energy performance, water usage, and so on. There are a couple of indicators that have to be reported. And then targets are coming up. So there are at the moment in the EED some suggestions, ideas, but there are national level targets that are coming up. And if you go to the next slide, you see immediately the German. I've taken this slide from the Uptime Institute. Probably it is still valid. Sorry, it was a year ago when I took it. But you see, it is flat. PUE, yeah, for after 2026, yeah, already 1.2 wide, the average now is around 1.5, 1.6. Maybe there are even worse cases, yeah. So which are newly built or they have to be renovated. Heat reuse is also becoming mandatory in Germany. Renewable energy consumption, there are target values for this, and also the French. They are not that strict like the Germans or the Spanish, but there are national target values, okay, which are mandatory. So very interesting what kind of pressure the data center community is getting and whether it is able to reach this. Okay, so these were what comes from the policy and what is our project goal. Okay, that you see the next slide. We said, okay, let's go max, okay, whatever we can. So very challenging KPIs we put for proposed. Next one, okay, next one. So PUE 105. So we said that let's jump from this 1.5 or 1.2 to 105. ERF means, sorry, everyone knows what is PUE? Or there is someone who doesn't know. I explain quickly. So it is power usage efficiency, practically effectiveness. Sorry, effectiveness. Sorry, effectiveness. So practically, it is comparing how much energy you are using for IT, which is the one, and compared to that, how much energy you use for other, say, for example, cooling, yeah, among others, cooling. Not that. ERF, energy reuse factor, more than 90. So practically, what it expresses out of the waste heat, how much heat you reuse. Okay? And PES, primary energy saving, we said 20% we are able to save, meaning that compared to a baseline, we are able to use for the performance, particularly this part, to use 20% less energy. Okay, let's go to the next one. How did we get to this part? Yeah? Just a little history. Okay, something like 9 years ago, yeah, 2017. Yeah, we started with the Boden type DC here, very much in Luleå or Boden, with RISE. And that time we said we are going to build the world's most cost and energy efficient data center, which is still pretty efficient, I think. That time we measured the 1.28. Okay, I don't know whether over a very long period, but definitely we were able to reach that. This was air-cooled. Okay. Then also there was an EcoCube project which went. So here we focused more on the architectural aspect, but there was a very bright idea, yeah, coming from RISE, and probably you will hear about that, to create holistic cooling control. So before that, there was a certain way of controlling the cooling, and that was a different idea. You will hear about that. Okay, zonal heat management. So we can do more with managing the heat inside the rack. That was in EcoCube. And then we arrived to HEATWISE, where we said, okay, let's look outside, what is around us. Yeah? That was also the purpose. Tertiary buildings integrated with data centers. These were only data center focus. And so heat maximization, this is a new story. There we were only doing energy optimization. Here we are doing heat maximization and energy optimization. Let's go to the next one. So how we do it? We have 5 pilots, 5 different tertiary buildings, and here we are experimenting. What are the opportunities with the technologies that we are developing? Let's go to the next one. In 5 countries also, right? One is here in RISE, and this afternoon you will have the chance to visit the laboratories to RISE. So the core of the whole technology lays in a hybrid cooling, which is a direct on-chip cooling with phase-changing material, liquid cooling, okay, and a closed rack and air-cooled. So this is hybrid cooling. And we expect that very high temperature compared to, at least for air, high temperature heat we are able to take out, which is quality heat. Okay. So besides that, you see here the technologies: hybrid cooling, closed rack, holistic cooling control, building integration, self-optimization, self-assessment, and other things. My colleagues are going to speak about the technologies. What we are promising to the world, the value side, more consistent and maximize the capacity of the chips, high quality heat, less capex, lower OPEX, compliance, and decarbonization. Okay, so that was my presentation. I'm very happy if you ask me questions here or online, reaching out to the project or H1 Systems to me personally. Thank you very much.
We have a questions and answer session for 15 minutes at the end. So we take it then, or do you want to take questions now?
One question.
Oh,
so what is the next project?
Yeah.
What are you thinking about?
It's like 2.0, maybe. Yeah, there are many. We can go to various directions. So practically, what we are aiming here is not a complete and industry-ready solution. Yeah, there is a TRL grade in the European technology technical readiness level. We are aiming 5. So practically, it means that we go until laboratory testing, validation. We do a little bit more, I think, than that, like, for example, at EMPA, where we try these technologies in a living lab, which is representing more of a real environment. But we still have this, and all technologies actually deserve further development, like orchestration. Yeah, you will hear about that. So when we are not focusing only about one data center, but maybe on more data centers, we can bring heat together. I think that is my answer to you. Yeah.
Watch this space then, yeah. Okay, moving on, I guess it's me next, isn't it? So I'm going to be talking about bridging the past and the future. Have you got my slides there, do you? Yeah. Here we go. Okay. Yeah. Okay. So I didn't introduce myself at the beginning, but my name is John Summers. So I am the scientific lead in data centers at Data Center Systems Unit, part of RISE. I have a number of hats. I have 2 honorary positions at universities. I'm also the chair of the Future Technology Symposium at the Open Compute. What I'm going to do, if you go to the next slide, then, yeah, this is the outline of the presentation. I'm focusing on 3 projects of the past. Attila has already mentioned one of them, the Boden-type data center. And the whole idea of this is looking at heat recovery and energy management, because this is what we're about today. We're talking a lot about the energy that these systems consume. So one of them is about air cooling with fresh air, leading to an efficient thermal management system, followed by some heat recovery from the air. So I'll show you some pictures of some of the things that we've done. And then there was another project which is involving heat recovery, and that was using fuel cells and immersion cooling in a closed loop. And we were harvesting the heat from the system for the local heating network. So with high temperature fuel cells. So if we zoom on to the next thing. So what are we talking about today? It's one of my favorite slides, and a lot of people have seen this many times. But in 1961, a very famous paper was written by a guy called Rolf Lander, who was a researcher at IBM. And the title of the paper is very, very telling. It's called Irreversibility and Heat Generation in the Computing Process. So what happens, we put a lot of effort into producing high exergy electricity. It has a high exergy. We put it through this system, which is our digital systems. And what comes out, most of what comes out is heat. But a little bit of it, if you go back to Rolf Lander's work, is a little bit of the energy based on the irreversibility of the computing process is transformed into information. And that's what we interact with on a daily basis. Now, the value of that information over the last 20 years has dropped. This is actually the real efficiency of the computing process. This is the real efficiency. So we've gone from 0.0005% to about 0.03% efficient. The incandescent light bulb was banned almost globally because it was only 5% efficient. Should data centers be banned on their efficiency? Yeah. So this is what we're talking about. We get a lot of waste heat, and this is not an efficient process. But this is a topic of great debate. So the irreversibility of the computing process is one of the reasons why we are in this kind of difficult situation. But if you move on, yeah. So it doesn't, the interaction doesn't work, does it?
Oh, no.
Is it just a PDF?
Yeah.
So you haven't got it doesn't matter, don't worry, because we haven't got time. But anyway, Attila mentioned, move on, David, yeah, just. Attila mentioned, so here there was behind this, there was a layer of images on here. Behind the slide is the Boden-type data center, which was a data center that we built in Boden, started in 2017. One of the reasons why it's good to run data centers up here is this kind of graph here. So this is the cumulative hours of the temperature being below 20 degrees. So here, the number of hours below 20 degrees centigrade outside is quite considerable. So, climate change is changing this, of course, that we're witnessing today. But 350 days per year in this region, on average, are below 20 degrees centigrade. And so if you're using outside air, you've got a great opportunity of free cooling, what we call free cooling. You don't need so when Attila put up the PUE really indicates if you're using a compressor or not. If you're using a refrigeration cycle, that means your PUE is much higher because the compressors are very energy demanding. Anyway, this is a project that we ran. So if you move to the next slide, One of the things that we did is we took control of the server fans. So we had ventilation units that were bringing in outside air into the data hall. And we had almost 1,000 server fans that we took control of. And we took control of that through a very clever arrangement that allowed us, here you can see the instantaneous PUE. And I say instantaneous PUE because originally PUE, when it was first written in 2006 by Malone and Bellardi, who were two people working for an IT company, nothing to do with data centers in a sense, put the focus on the infrastructure, not on the IT. And they wrote it as the ratio of two powers. And that's why it got the name power usage effectiveness. But it's actually the ratio of two energy values. So when you talk about, I've used the word instantaneous, but if you look at the ISO PUE, it talks about an interim PUE, which is the energy over a particular time. But anyway, what we did is we say over 10 minutes or 15 seconds, you can measure the PUE based on the delta T. Now the delta T here is the temperature difference between the front of the servers, the air coming in from outside that we're supplying to the front of the servers, and the temperature at the back of the servers. So as we took control of the fans, that we slowed them down, we said, come on guys, you don't need to work so fast, let's run a bit hotter, slow down, slow down, slow down. Our delta T went up. And because everything slowed down, our PUE, our instantaneous PUE dropped, because the energy going into the moving parts that are moving the coolant dropped. So the consequence of this is that we developed what was called a holistic cooling control, where we synchronized those server fans with the ventilation fans. And so everything was synchronized and allowed us to take good control. So if we go to the next slide. So here you've got two traces of workload on the data center. The difference between these two is that this is not using holistic cooling control. This is using and the exhaust temperature of the servers for all 480 servers that was in that data hall was constant. And if we go on to the next slide. So by raising the delta T, we have a lot of hot air in the hot zone. We're talking about 50 degrees plus. So what are we doing with that? Just venting outside? No, why not do something more intelligent with it? Why not capture the heat coming out of the hot area? The interesting thing about this data center design is it was cold aisle containment, but on a slab floor, but the data center was the hot aisle. So the cold air was contained. So as the air came in on the front, it came into the cold area. The back of the data center, which is here, was actually the hot area. And so we put a ventilation component in there and pushed it through. This here is biomass drying. So we're going to try and remove humidity, reduce the humidity of biomass so that it actually is more useful for an energy system using the data center's hot air. And so we ran that. In the next slide, you can see the temperatures that we were getting out. So we were getting, well, we had over 50 degrees in the hot aisle, but we were getting 42 degrees at the ventilation. And this is not well insulated. So by the time it got to the unit here, we were seeing 36 degrees centigrade. And then that was passed through the biomass dryer. So we were able to reduce the humidity. It doesn't say here, but the energy reuse factor was 42% on this system. There was an 8% reduction in the moisture content in the biomass, which is useful, very useful. And the project, which was Arctic DC, I didn't say that was the second project. It was an 8-year return on investment for that approach, using the hot air. But I mean, that's something, the unfortunate, with the weather, with the actual climates that we have, we won't get that hot air all the time because the hot air is recirculated sometimes inside the data center because the outside air is too cold. You don't want to bring in -20 straight into your servers. So you have to mix the hot air. So this hot air is not always available. So it's not an all year round approach. This was run in the month of September up here in the north of Sweden. So if we move on to the next This is a dynamic. If it was running through PowerPoint, you will see this. This actually is a movie. But we did here is this is actually our this is all changed now, but because there's a company here called Renter. But this is the side of the building where down the road where we have the facility. And what we did is we produced a containerized system. So the top part here are fuel cells, and the bottom part is the data center. So you have an energy producer on the top, and on the bottom you have an the actual data center. And 12 meters or 15 meters because of regulations, there was a huge amount of biogas. So we stored biogas here because there's no piped gas here. So the biogas was feeding the fuel cells. The fuel cells were producing electricity for the IT system. And the reason why we're right adjacent to this building is the other side of that. The other side of this wall here is where the district heating comes into the facility. So we could connect to that and provide heat to the facility. So if we go on to the next slide, we can see inside, these are the fuel cells, solid oxide fuel cells. They operate at about 750 degrees centigrade, good temperature. They exhaust the gas, which is mainly CO2 and water vapor. So to operate them, you need fuel, air, and water. And then it's an electrochemistry process. It's a continuous flow battery. And these are 1.5 kilowatt units each. And the exhaust gas is pretty hot. So you're around about 85, 90 degrees. We can capture that heat and then use that heat in the adjacent building. The other thing is that they consume a lot of air. So they take out outside air, which is really cold. So we use the data center that it's actually powering to provide to warm up the air to the fuel cells. So it's an integrated system. So if we go, you can see the temperature map there. But here, this was actually the data center. So we used an immersion tank. So we put a load of open compute servers inside an immersion tank, which is a dielectric liquid. And we ran this, we actually got good data for 6 months of operation, which is part of the agreement on the project. I didn't say what the project was called. Again, it was an EU-funded project called We District. And it was about renewable sources of energy for district heating. And the data centers do produce renewable sources of energy. But if they're running off biogas, which is locally produced, then that biogas has reduced the methane that would have been emitted to the environment. We're still emitting CO2, but CO2 is better than methane emitted to the environment, but it's a reduction in carbon. Anyway, so you can see that we connected up the fuel cells to the power supplies. Unfortunately, it wasn't fuel cells run on direct current. The data center, the systems here run on direct current, but we had to transfer to AC and then shift down below because the container with the fuel cells is on the top, shifted by AC current and then converted back to DC, unfortunately. But if we had the opportunity, if we could have done this, we would have done DC to DC directly. So on the next slide, this is actually operation. Some interesting things to note here. So we took control of the 9 fuel cells. We can change their power level. But what we did is we put a workload on the data center, and then we said, can we get the fuel cells to follow the workload? The workloads, is demanding power. The unfortunate thing about it is they're very laggy. So here you can see 3 fuel cells on each of the 3 phases. So that's why there's 9. We put 3 on phase 1, 3 on phase 2, etc. But you can see that the demand from the data center is changing here, but the fuel cells are not ramping up fast enough. They have a ramp rate of about 35 watts per minute. IT has a ramp rate which is pretty much higher, much higher. So they can't keep up. And then, of course, when you drop the workload, when the workload drops, then they are overproducing. So you're underproducing and overproducing. So the way around that was to be grid parallel. So we were connected to the grid so that if we didn't have enough power, we could pull it from the grid. If we were overproducing, we could push it back up to the grid. So, and then the biogas storage is over to the right there. The challenge here was that this was stored at over 100 bar, so it's like high pressure. We had to reduce it to 26 millibar, I think, which is a big pressure reduction. And you're doing that in a cold climate. It's rather challenging. So when it's minus 20 outside and you're expanding the gas, it cools down even more. On the next slide, we have the actual results of this. So there's a lot of data here, but what I wanted to concentrate on is that we monitored the power that we were using on the grid. We monitored the power of the energy that was generated by the solid oxide fuel cells. We monitored what the IT required, and we monitored what the infrastructure required in terms of energy. And we were able to show that 79.2% of the energy required to run the system came from the biogas. The other 21% came from the grid. The other thing is that the interim PUE, because it wasn't 1 year, we only ran for 6 months. So I've been very faithful to the ISO, because the ISO standard for PUE says it should be 1 year worth of data. So that was 1.16. So that meets your target until 1.2, doesn't it? That's good. And the IERF, I used I again because ERF should be annualized as well. The energy reuse factor is what you use over 1 year, was 9.5%. So that's the amount of energy that went in, of the energy that we consumed from the biogas, how much of that ended up as heat in the network? And that was 9.5%. So it meets your requirement as well, or your target on the, so pretty good system. So on the last slide, I think I have a few takeaways here. Holistic cooling control, taking control of the server fans, allowed us to use outside air temperature. We could lower the temperature supplied to the data center, and we could get very efficient and get a very high delta T. We took control of the fans. Some people will say, whenever I gave presentations on this, they said, "Are you crazy taking control of server fans? Because, you know, isn't that, we should let the servers demand what they want." But actually, there is an initiative which is called OpenBMC. And OpenBMC, on a lot of servers now, you can program your own algorithm of control of your fans in your servers using OpenBMC. So that wasn't such a daft idea, because OpenBMC came after what we were doing. We had to do it a different way. We didn't have access to OpenBMC. The immersion systems that we showed were rejecting heat up to 40 degrees centigrade. Some people say that with the immersion systems, you should be able to get higher temperatures. And then the solid oxide fuel cells were 55% efficient. That means that the calorific value of the gas, 55% of that became electricity. The losses are in the heat that is generated. And an interesting thing to note from this, a general discussion point from this, it's an edge. They're containerized. It's a containerized data center. You could think of this as running in island mode. You could think of this as supplying, I love this, can we use hydrogen to try and reduce the carbon intensity? So do we add hydrogen to the mix? Because if you add hydrogen, the fuel cells run on hydrogen. Eventually, they just have a process of getting the hydrogen from the methane to run. But if you could add more hydrogen to the solution, then if you could add hydrogen to the solution, you could reduce the carbon intensity of the energy generation. And putting it in an urban area is quiet, not very noisy. Fuel cells are not noisy. The immersion tank was not noisy because there were no fans. And it will take the load off the urban grid, but it would also provide heat locally as well. And on that note, I will finish with the last slide. And this would be an animated flyby of our institute. But I don't know how we're doing for time. Yeah, probably a bit late. But anyway, let's take some questions a bit later, unless there's any quick questions now. I always Tor has one here. What have I said wrong?
No.
What did I miss?
Which project is the best one?
Of these three?
Yeah.
Depends how you measure it. If you measure it by PUE, then the Vodafone data center, because we actually supplied 1 year's worth of data to the EU code. We were a participant and an endorser of the EU code of conduct, which we'll talk about a little bit about that later. And our PUE was officially 1.016. So, a world record, yeah. but does it really matter? I mean, it's, yes, well, yes.
Just to follow that up, I think the most significant element of that project was demonstrating the importance of controlling the IT.
Yes,
Having that essentially feedback function between the facility and the IT, because it's the only way we're going to be.
the holistic cooling control. I mean, the principle is being used, I think, in the HEATWISE project, holistic cooling control in some respects, yeah. I agree.
There was an online question. Can I
There's an online question,
read it?
yeah, go ahead.
But before I want to highlight one thing, like I'm involved a lot with the European data spaces nowadays.
Yeah.
And when I actually check the open data sets for the data center related, like IT related data sets, I think the Budentype DC1 data set is the only one that I could reach. There are more, of course, like we are also doing our best to share the open data sets as much as possible in EcoCube project and others. But I would say that 1 year of full data set, we benefited from it in EcoCube and in other projects. I think it is, I'm just trying to highlight the importance of this. The second thing is there is a really nice question online. Actually, Mark and I, we were just discussing about it in the car. So I think it's a really nice question from Mats Eriksson. How does the increase of the operating temperature of the servers impact the expected lifetime of the servers and IT?
Well, yeah, I mean, that's a challenging question. There is a thing called the X factor, I think, which is in the ASHRAE, but I don't think it's the actual temperature of operation. It's more the temperature variability that's more of a problem. Because if you think about, you know, temperature fluctuation going up and down, you're going to be stressing the electronics. And, you know, material will expand, contract. That's going to cause failure. So I think that would. So there's another side to that question. You know, when you run IT hotter, it does demand more power. It needs more power because of the current leakages. So the question is when you are maximizing your heat in your HEATWISE project, are you sacrificing that the fact that you're drawing more power because you're running hotter, and therefore. But it depends, and there is a thing in the industry which is combined heat and compute. So that depends how you word it. Is it combined compute and heat, or combined heat and compute? Which is more important, the heat or the compute? And that's something that I think is something we should discuss today.
We should discuss the X factor. So.
The X factor, yeah.
It's a complete fudge.
It's a, yeah, but I mean, it's all. But what can we do? We don't have the reliability physics are not. They're not well understood. So. I mean, we do have some good models, but it's statistical, isn't it? Yeah. So to Max, we don't have good data on it. So unfortunately, but there is this X factor, which Mark says is a little bit of a fudge. Okay. So Mark's saying we should always look at people's genders before you actually. Yeah. Okay. Right. What's Thanks for the interactions. Who do we have next?
We have Frederick. So
Frederick. Oh, of course, yeah, Frederick. Yeah, sorry. I forgot all this. Yeah.
Thanks so much.
Mr. Holt.
Hi, everybody. Let's see, we got some slides up there. So you'll do the clicking over there?
Yeah.
Cool, there we go. Thanks. Hi, everybody. I'm Fredrik Engström. I'm the business area manager for district heating and cooling at Luleå Energy. So that's the municipal local energy company, basically, where our office is right just a few hundred meters away. So that's Luleå. No, I'll get there. I also have a connection to the university, actually, same kind that John has as an adjunct professor at fluid mechanics at the LTU. Let's jump to the next slide. Yeah. So obviously I come from the heat offtake side. So we're responsible for the district heating in Luleå. It's one of the bigger grids in Sweden and especially one of the more grids with the highest penetration. So we basically serve most of Luleå with district heating. So a quick 101 on district heating in case you don't know that. You can also challenge yourself with finding errors in this picture. I stole it off the internet, of course. Some arrows here on in the wrong direction. But basically, district heating, the key thing is it's heating from a distance. So typically you would have a power plant in the typical setup, a big central power plant. that maybe is combined heat and power, not combined heat and compute in that case, that would supply heat throughout the city, for instance. So you would pipe your hot water out to all the buildings and those who want that heat, and you would get cooler water back. So also here we talk about the delta T, that's sort of a key performance indicator for a grid. So in the typical setup, one big central heating facility in Luleå, it's owned by Luleå, which is a partner company by us and the big steel company. I'll come back to that. But we also have a number of additional heat sources across the city, both for peaking and redundancy and so on. So most of Sweden, most of the world, I guess, district heating grids are fairly old. So here it's been around from the 70s. And that means sort of you designed it for buildings of that time, and most of the buildings in cities in Sweden are typically older rather than newer. And that says they would consume more energy per square meter than a modern building would do. And also these grids were designed therefore for quite high temperatures. So typically these grids are designed for supplying maximum 120 degrees. Now we're backing off from that. But if you would do this from the beginning with modern houses and modern technology, you can go much lower in temperature. What limits the sort of temperature how far you can go down is that basically it's not just heat, it's also hot tap water. And of course you want that to be 55, 60 degrees maybe when you open the tap. So you need something higher than that to be able to get that hot tap water on, unless otherwise you need some other technology to support that. And anyone found the error?
Far right side.
Yeah, so that's correct. But here it's hot water going into the heating plant, so that can't be right. So almost good. Okay, now we can jump to the next slide. So this is the core of the Luleå district heating. So for those not familiar, where the sun is shining beautifully, that's across the big steel plant in Luleå. So SSAB is the company name. And then to the left in the picture, you see it says Luleå Energy. That's our big energy storage. So that's 1,600 megawatt hours of storage that was built a number of years ago. And further to the left with the big chimneys, that's Luleå. So that's the CHP, the combined heat and power plant in Luleå. And you can click the next. So basically, that's the core energy that we get gases from the steel plant into that CHP, and that's distributed out across the city. Typically annually we produce 900 gigawatt hours of heat. But this is, as John said, it's cold here, but it's also warmer sometimes in the summer. So warmer summer days, we're down to maybe 30 megawatt in heat, or we could even go less. But then in the peak winter, we go to 300 megawatts. So it's a huge dynamics here in sort of the hour by hour heat demand. And as I said, these grids were typically designed for 120 degrees. We have decreased that maximum temperature, of course, then we increase the flow. So actually this year we're down to 99 degrees. The reason for this is actually to be able to accept more sources of heat, because there's a big energy transition happening here in Luleå that I will talk a bit more about. So if you click the next thing. So those 900 gigawatt hours, in a few years' time, we'll be losing 90%. I will let that sink in for a while, and then you realize my challenge. And why is that? That's because this steel plant is shutting down. It's an old steel plant, been around for decades. It's a blast furnace-based steel plant, therefore it emits carbon dioxide a lot. That will be shut down. So we need to replace most of the heat because we basically burn the gases from that steel plant. Fortunately enough, there's a new steel plant being built So we get more new opportunities to get waste heat from the new steel plant and also other industries. It will not replace everything that's being lost, but a big chunks of that. So of course, we're looking for more waste heat sources to be added into the system so we can gain our 900 gigawatt hours. Probably we'll have to build some new boilers for ourselves as well, just to make sure that we have those 300 megawatts when it's cold. So you can jump to the next slide. And I said in the summer, maybe 30 megawatts and in the winter, 300 megawatts. So just how do we think about that? Because it has implications for data centers. So all the hours of a year sorted in the most demand to the far left and least demand to the far right. So the area under this curve is basically the 900 gigawatt hours that we need to supply. How do we do that? Yeah, typically we would have some base load. Current system, that's the CHP. That takes a big chunk of this. And when that's not enough, we need to add some intermediate source, which could be maybe wood pellets or electrical boilers. And then maybe for peaking, we actually burn a lot of oil for those coldest hours of the year. So we still do that. But of course, it's a small amount of energy, but it's still expensive and not good for the climate. And what you should also think about here is that the base load is typically your cheapest heat, because that's what you use the most, and all hours of the year. And when you go upwards here and to the left, you would find typically more expensive sources. But if it's just a few hours, that's probably okay. And we're famous in Sweden because we have the cheapest district heating by far in Sweden. So the challenge is, can we keep that? But thinking about data centers then, where do they fit here? So typically data centers would be some kind of base load. So it would go to the bottom. That means we are not prepared to pay very high prices for that heat. If it would be just peaking, then we would be prepared to pay quite a bit. But I guess data centers would be interested in more hours rather than fewer hours. We can jump to the next slide. So as I mentioned, we need to replace 90% of our heat. Unfortunately, there are new projects making that happen. So the big thing is the new steel plant. That's an arc furnace-based steel plant. So we'll get substantial amounts of heat from that. And we are in those negotiations now with the steel company. There's also a big plans from LKAB, which is the state-owned mining company, who have big plans for a project to get rare earth metals and or elements and also phosphorus to big plant like that. Big thing in that plant is you need to produce sulfuric acid, and that also gives a lot of heat. So then you have two good heat sources that we could use. So we are in close discussions with them as well. And then there are a few other projects here that may or may not happen. But if you click the next thing, this is where data centers actually could be a thing. If you click the next. But there are a number of question points here that are important to understand. So as you saw, we operate the grid up to 99 degrees. And I didn't mention, but the return temperatures is typically 40 to 50 degrees or so. So where in this temperature range does the data center fit? As I understand, the data center will probably not supply 99 degrees. If it would that, then it would be all good, because then it can be used all year round. I've been in contact with data center suppliers who could supply 75 degrees. So that's sort of on the low range, but still interesting. But then you need to understand its district heating grid. So where in that grid will that data center be? If it's close to our centralized part of the heat supply, you could preheat the water to 75 degrees and then top it up to 99 degrees, and then that should probably work quite well. If you're far out in the grid, we have boilers like that. Is it useful for us to get 75 degrees? Yeah, during the summer, all good. During the winter, maybe not so good. So that puts some challenges to this. Then, of course, obviously, you can take any heat source and you can use heat pumps to raise the temperature. And of course, that's done in in many places, not just from data centers, becomes more expensive heat. So then it's a question, what does it compete with? And of course, it goes together with what I talked about in the duration curve. How many hours can you operate? For what price do you get heat? So that could also be a bit of trade-off. But the key thing here is what kind of temperatures will you get off the data center, and where does it fit into the grid? A small thing that could be interesting also is to use the return heat to feed our, we get colder water back. You could put heat into that. And we actually use that heat also for clearing ice off streets downtown in Luleå. So when you walk in Luleå, you would find that why is there no snow here? That's because we heat it with the return temperatures. So it's not a free energy, but it's sort of cheap energy. And that could be a supply from data centers, but then it would be quite cheap. So maybe not a big revenue stream, but still supporting the sustainability. So, of course, when data centers now develop, temperatures maybe rise with good cooling and so on. So I think the opportunities are more and more getting there for data centers, but it's not just to plug it in and run it. So there are some things to think of. Yeah, that's me. I'm happy to take questions on that. Or should we say that?
I have a question, if I
Sure.
can. Yeah. So, Frederick, I'm looking for a house in just I want to actually start with you for starters, because I want to understand the problem right after the entries. Like one of the things that when I started working in this project, I was a bit not sure about like what the building and district heating needs. It was more like blurry for me. I was looking at all the problem from the data center side. Now I'm privileged to work with great teams to understand better the building and district side. But from your point of view, in the future, are you still looking for a more centralized solution? Because more I understand, like when we try to transfer this heat, like we need to higher and higher temperatures. Are you thinking about a distributed different heat sources? You answered it a bit, but how distributed you imagine it for the future? Because one last thing, for the online audience, maybe it's good to say the average temperatures of Luleå is 2 degrees, right? In a year. So I'm Turkish myself, and when it's minus 30, 35 outside, I'm still sitting inside in my home with my shorts and t-shirts, and I enjoy it so much. So I just want to be sure that I can still enjoy it after we shut down the steel plants. Like I'm just thinking out loud.
We also have warmer days in Luleå.
Yeah.
Especially last summer.
Let's say.
That was pretty good. No, good point. And I will say things that I forgot to mention maybe, but will we be able to heat Luleå in the future? Yes, absolutely. With these new waste heat sources, we have really good opportunities also to be sort of the affordable solution. Maybe can we guarantee we'll be the cheapest in Sweden? Not so sure, but we have good prospects to be very affordable still. So that's one thing. I should mention, maybe I didn't mention that enough. As I said, this is an old district heating grid. If you would build it from the start, there are new district heating generations where you are much lower in temperature. Yeah. So you can do that in different ways. You can have this sort of a small heat pipe for the tap water, and then you can have much lower temperatures for your heating. And of course, then you have a much better fit to more waste heat sources when you go down in temperature. So that's important to understand. We actually have parts of Luleå that run at the lower temperatures, so maximum 80 degrees. So that works. And of course, here you can start to think about different combinations of a decentralized data center that happens to be in a place, because you also need an electrical grid, which is close to a part where you can support one of those areas maybe. And of course, Luleå is expanding as a city, so you could also think about new parts of Luleå where we could possibly make sort of run different temperatures. A bit more challenging to integrate that into the total system, but it's still possible. So we're definitely open for discussing data center applications into the grid.
I need to improve the question with one more thing. I think it's relevant. Sorry. Just again for the audience, when a Swedish person says there was hot weather, it was 20 degrees, 20, 25, just for, oh, okay, just for your information. But the curve that you showed, like there was that red zone, which is like the static mode, like more or less you don't touch. If I know the data center market a bit, I think we are that stubborn people who doesn't like to change the load a lot. Like we are trying to make it flexible. But how flexible we can be, I think more EU research we conduct, maybe we can train ourselves to be more flexible. But my question, during a really warm Luleå day, when it's 25 degrees, everybody's suffocating and so on. What we can do with our waste heat? Like, do we have some alternatives to if there are some sources that you can shut down, like data centers? Where we can actually, how we can use it? Can you elaborate it a bit more? Like when it's really hot, like what we do?
It almost never happens. No, but that's a good point. And actually, as I said again, I'm also responsible for cooling. So we actually do cool things in Luleå, actually all year round. Today we are cooling buildings in downtown Luleå, because that's how buildings work basically. So we actually need cooling all year round, that you would think. Obviously in the summer it would be more cooling. We don't have that in our cooling system right now, but we're investigating that, because there are, you can do absorption cooling based on the district heating. Then you would need to run it a bit hotter in the summer, but as you can understand, these industries that we are already collaborating with, they would run also. They don't want to do like that. They want to go base load, as all industries. So we would get that heat all year round. So in the summer, we would have a cooling issue. And if we could use that to run absorption coolers for cooling buildings, that would be sort of a good way to do that. Also, another thing that I'm also the CEO of a wood pelletizer plant that sits also is part of this symbiotic system where we run on the chimney gases from that CHP goes into drying the wood that goes into the sawmill dust, basically goes into the wood pellets. Very efficient system. Of course, when that big CHP needs to shut down because it's not getting any gases anymore, we need to transform the cooling, or sort of the drying for the biomass. That's also usage of, district heating. And in the summer, there would be a surplus, so then we can run that full speed, basically. So that's also something we're looking into. So, yeah, there are our usage for heat in the summer as well.
So more questions. Let me help you.
I was thinking we have talked about the rise about so-called heat transformers. I'm not fully into that technology, but as we have understood it, you use part of the heat to upgrade the heat. Instead of using electricity or gas, you use the heat. And this relates to the absorption chiller. So have you looked into that type of new technology, heat transformers?
It's a heat-driven heat pump. Yeah.
Right. Yeah. No, I know about that technology. We haven't investigated it ourselves because it's, maybe from our point of view, it's on the potential heat supplier side. So basically, if you have a data center and want to supply to us, you need to investigate, can you reach it to the temperatures that are useful for us? So we haven't looked into it into detail, but that could be something to investigate to accept more waste heat sources. Yeah, that would be interesting. Yeah, we have a good example of a data center not so far away from here. We're not accepting heat from them.
We could.
Thank you, Frederick. I have several questions. One is about the heat storage. Like, is it a seasonal or it is a short term? And what is the amount or ratio compared to the demand? Yeah. And because that is obviously could be a good source, if there is population. Okay. The other one is about the temperatures, because I could not follow, because you were mentioning 120 degrees and 90 degrees, 70 degrees, I understood that there is a potential that you go down with the temperatures and then connecting the data centers with the returning probably pipe. So can you help me out with that? What is the chance that you can lower these temperatures and to go in the third or fourth generation?
Yeah.
And that is obviously not only the heating, but it is a lot of investment on the user side, right? It's the heating system that determines what is the heat that has to supply.
Yeah. Okay, so let's see if I can remember all those questions. So first of all, the heat storage, yeah, it's 1600 megawatt hours. Maybe that's compared to the 900 gigawatt hours. So basically that's hours size of storage. Big thing with that is that we can run it at up to 116 megawatts, so we can actually force out a lot of heat from it in a short time, but that would, last for 10 hours. Typically, we're not going that high, so we do it a more balanced way. But basically, what that's done is what we get from that is we can basically managing disturbances and to some extent also optimize how we run the grid. So if we have a peak, we can use the energy storage if it's full instead of maybe starting an oil burner. So that would be good. But it's basically day-to-day usage like that. A big thing in district heating is seasonal storage, and there are solutions for that as well. But typically, they are not on the size that matters in our system. Because if you have 900 gigawatt hours and talk about the seasonal storage, it would be on the order of hundreds of gigawatt hours. And typically, this seasonal storage is what I've seen is on the order of a few gigawatt hours. So it's a bit too small, but that's the technology for that would be very interesting. Coming back to the temperatures, and now you need to stop me when the time is up because I'll just go on. So if you go back to the one with where you had the temperatures. So maybe I can, yeah, this one. Yeah, so what I said, originally, a district heating like ours, which is old, the grid, was designed for 120 degrees and run like that for up until, a number of years ago. But during the last few years, we've done a lot of, we have reinforced the grid because when we go down in peak temperature, we need to pump more water out to our customers to supply the same heat because they still need the same basically megawatts to get the heat. And of course, there are other benefits. Our heat storage runs at 99 degrees, so now we sort of are we're on the same level. 74 degrees, that the supply temperature is sort of the least we can go because we need to supply that hot tap water in the summer and so on. So basically, we're not lower than that. But what we could do, we can continue to lower this. We're on the grid in Råneå, which is a village outside Luleå, that runs on 90 degrees without a problem. But at some stage, our customers, all their systems were designed for 120 degrees at some stage. So of course, where you have an old grid with older buildings, you will run into problems at some time. But actually, it works to go down quite a bit. The return temperatures are on the order of 40 to 55 degrees, depending on the season. So it's the delta T here that we are using. And of course, data centers, it could have quite a bit here, but that's on the return. So that's sort of the coldest we need to go. So that's not energy we can use, basically, because this is where we go from here upwards, not here downwards. So if the data center supplies 50 degrees, maybe it has to be cooled down to something lower. We can't supply that cooling, basically. So you need to be able to to be directly connected to the grid, you need to work in this range, basically. But then you have this, you can basically put heat into the return and we can use it to clear ice and so on. But that's sort of a low value use of heat. So it's not a big revenue stream, but it would be nice, maybe. We've also have you can run greenhouses and things like that, but that's sort of other offtake basically than district heating. But then, as I said before, new district heating systems, next generation district heating systems, you have all other possibilities. I think if you can supply basically 50, 60 degrees, then you can basically run it if you have designed the buildings and everything around that. I'm not sure how far you need to cool down then, but then you need to have a separate solution for the tap water. But that's a smaller stream, so that could be still working. Was that all the questions?
Yeah.
Yeah.
Just a comment, would it be,
Sure.
I mean, obviously, the best way to do this, because obviously running at a high temperature, I've got a lot of losses, so you must have seen a little bit of reduction in energy losses by dropping the temperature.
Yeah, no, that's a good point.
And then, but if you run much colder and upgrade at the point of use rather than just connecting directly to the heat network, so you use heat pumps at the point of use rather than, which is the concept of the 5th generation, I guess.
Right.
That would be, what kind of savings would we be looking at? And is that where we might go with Luleå, perhaps?
Yeah, so what John is saying, if you didn't catch it in the microphone, is that basically you could supply heat at a low temperature and then have local heat pumps to basically get the temperature that you need.
Yeah.
And of course, running the grid at a low temperature would reduce the losses. And of course, we see that, and that's one of the reasons why we also would like to go down. Absolutely, so that's possible. But sort of converting our existing district heating system, and important to understand, it includes all our customers. We have 10,000 households connected, serving 30,000, no, basically including apartments, more than 30,000 households connected, and 1,500 larger consumers. So it means converting all their systems. And of course, it's basically their cost, but it would be sort of looking at the system cost, it would be huge.
You'd have to do it all in one go, wouldn't you? As well?
Yeah, exactly. You can't just slow the temperature and wait. So that's a challenge.
Can we take the questions at the end, because we are a little bit late? We will come back with the questions. Yeah.
Thank you so much.
Yeah.
Thank you.
Yeah, the questions were righteous, so I'm giving it back to Mark and John in this case.
Do you want to skip this, Mark?
No, I'll do it, but rather than doing a Q&A, I'll just talk, John.
Do you want to just tell us a little bit about, because people don't know perhaps the EU Code of Conduct.
Yeah, exactly. So I'll talk.
You've been involved in a lot of the energy efficiency directive as well.
I was going to
recast. Yeah. Okay. Thanks a lot.
Yeah, so slight administrative error on my part. I didn't realise I was supposed to be giving a presentation, so I have no slides. But what I will do is introduce myself, and I think then lead into the code of conduct, which is what I'm here to talk about. So firstly, I'm an engineer. I've been working in the data center sector for about 30 years. I've run data centers, so I think I come from a fairly unique perspective. I've run data centers, and I've run some very large data centers around the world. The largest single building I've run was 64 MVA. Okay, that's the incoming supply. That gave around 40 megawatts of IT. So think about that for a bit. That's a peak PUE of about 1.6 or so. And that is what we design buildings to now. So I do a lot of work with an engineering consultancy called FutureTech, who design data centers. That's what they do. They designed co-location type data centers, and they design AI data centers. In fact, they've just been bought by Nscale. So, they are very focused on the AI platforms. But think about it. When we design data centers at the moment, we're designing, this is still the case, for a peak PUE of 1.6 or so, 1.5, 1.6. And that sounds horribly inefficient. But what you've got to do in the data center, you've got to cater for the worst case scenario. So, we've been joking about heat here in Luleå. Maybe it doesn't get above 25 C. I don't know, but I'll take that as a sort of a guide. But elsewhere in the world, obviously, you've got far greater fluctuation. So you've got to design and build your data center for the worst case scenario, which might be 40 degrees. It might be 45 degrees in the summer. So you're having to run some mechanical cooling almost certainly at some point, at least in the traditional data center. So, we're pretty inefficient. So I'd like to bear that in mind. Whilst we have, this idea of leading edge research and taking the PUE data, 1.05 or so, in the real world, we're aiming at about 1.5, 1.6. And again, that's peak, not average. So, there is a difference. So, I thought I'd say that just because I sort of, I'm coming to this from a practical delivery perspective. Going back to the theme that we've got, the EU Code of Conduct. Who's actually come across it? Okay, quite a few of you. So the EU Code of Conduct was an initiative that was started off in about 2008 and published in 2009. And the idea was that it was a European Commission funded project to develop a series of best practices that people could apply to their data centers to reduce their overall energy consumption. So the correct title is the EU Code of Conduct on Data Center Energy Efficiency. That's been going, again, first published in 2009. I've been the editor and the chair of the Best Practice Committee since 2013. You know, I haven't got time off for good behaviour, unfortunately. So I'm hoping to.
Time to misbehave.
Time to misbehave, exactly. And so, and again, I think it's been proved to be very, very useful. It is not something that's, you don't have to follow it, but if you do follow it, it's very useful. It gives you a very, very good guideline on the kinds of behaviours you should be looking to introduce into your data centre to reduce your energy consumption. And as we all know, the biggest cost over time in a data centre is the cost of your energy to support that data centre. It does change every year. We're actually a bit behind on this year. We don't have the 2026 version out there yet. We do have the 2025 version out there. So if anybody wants a copy of the most recent version, just let John or Chate know, and then we'll get you a copy. But we are due to produce a new version. The Code of Conduct has kind of been successful in many respects. It's referenced in the EU taxonomy, which is self-referenced in the CSRD, so the Corporate Sustainability Reporting Directive. And what the EU taxonomy tells you how you should be reporting your sustainability metrics for corporate sustainability purposes. And the Code of Conduct is referenced in that taxonomy in terms of what you should be reporting and how you should be reporting it. And effectively what it does, it references the ISO standards, which are in the 30134 series, which includes PUE, WUE, ERF, REF, etc. All those KPIs that we commonly use. Going back to PUE, PUE has actually just been updated. I don't know if anybody's aware of that, but the new version was released earlier this year, so it is a new version. So if you're talking about PUE, you should always be referencing the ISO PUE and the most recent version of that ISO PUE. So you'll find a lot of people talk about PUE without really understanding what it is. So always be sure when you're talking about it, reference the standard. Because if you're not referencing that standard, you're not referencing PUE. Just as an aside, I will get back to the Code of Conduct. As an aside, PUE is a useful operational metric, but it does not measure efficiency. It doesn't measure overall efficiency of the data center. I always compare it with a pint of beer. PUE measures the froth. The bit that's interesting, the bit that consumes all the power, is the IT load or the beer. So that's just my view of PUE. Nothing wrong with it, as long as it's used in the right way. So back to the Code of Conduct and the sort of premise of this particular presentation. How do we sort of adapt the Code of Conduct for AI? Well, to some degree, we don't necessarily need to. And one of the things that the Code of Conduct is very non-specific. It doesn't reference any particular technology. It doesn't tell you you've got to use direct liquid cooling or immersion. It says what you should be doing is evaluating these new technologies as they emerge and determining whether they're appropriate for your particular use case. So we try very, very hard not to be, not to define sets of requirements, not to particularly focus on any technology, but more to encourage people to look at opportunities for improvement. So again, it's a series of 100 and some practice. I've forgotten how many there are now, but it's over 100 best practice, something 160, I think, approximately. Yeah. So it's a lot to go through. And if you're ever, struggling to sleep one night, then try and read it. I challenge you to get to the end. Won't happen. So yeah, there's a lot in that, and some of these are mutually exclusive. If you are purely using air cooling in your data center, and there's nothing wrong with it. If you're literally working at sort of 10 kilowatts or so a cabinet, something like that, why not use air? You don't have to go to the added expense and cost of direct liquid cooling, for instance. So you don't have to. So some of these are mutually exclusive. You can't apply all the best practices in every case because some literally do not apply. We mention HPC. We don't mention AI specifically, but we do mention HPC. And of course, with HPC, as the power densities in the IT stack increase, then you need to go to different approaches to remove that heat, obviously. How you do that, it can be done in different ways. It can be, yes, of course, direct to chip, it could be immersion. It's almost certainly going to be a combination of liquid and air, however you go there. There is no liquid solution on the planet, as far as I'm aware, that can be 100% efficient. There's always going to be some level of air cooling. And how we manage that combination, that hybrid cooling system is actually really quite complicated. We do suggest the holistic method. We do suggest actually looking at the IT stack and saying, actually, can we do a better job of understanding what's happening in the IT stack and maybe, tuning how we make the building work in terms of cooling based on what the IT stack's doing. And I think as we go into the increasing power densities associated with AI learning, particularly, then we actually need to be far more aware of what the IT stack's doing. I don't know if you've come across this inrush problem that we've got in the AI, big AI centers. So when a workload starts, there's an incredibly rapid ramp up of power, and it can be tens of megawatts. And actually, in some cases, particularly in the States at the moment, that's actually being pushed back to the grid. So it's causing grid instability. So you're now seeing people introducing supercapacitors, etc., UPS that have more of a best pipe function, as well as just the battery autonomy. So UPS obviously is designed to protect you, well, designed firstly to condition power, and then protect you in the situation where you have a power outage. It gives you a bit of battery ride through before your generator start, which is great. But because we're now getting this inrush challenge with very large workload swings, then people are talking about putting either again supercapacitors or increased battery sizes on the UPS to basically provide some sort of mitigation against that inrush, so we're not putting it back to the grid. So it's a problem. But the thing I would really caution against, and we need to be very careful when we talk about the code of conduct, we need to be very cautious of not changing the way we run regular data centers. Co-location, the standard co-location in cloud isn't going away. We're not certainly going to be doing everything on GPUs. That's not going to happen. So we need to be very careful that we don't start making changes to what I would call your more standard data center based on what we're doing with AI. So you're still going to be seeing people building co-location, building it for an average of, I don't know, sort of 20, 30, maybe up to about 50 kilowatts a cabinet at the extreme end, which you can still cool with air. But we shouldn't be, introducing best practices that are really only specific to AI. So will we see the code of conduct change? Probably yes. But I think we're also going to be very, very cautious about introducing something that will not be relevant to the entire sector. And I think we're going to see increasingly the code of conduct being almost being sort of a choice of individual practices, not all of which can be applied. And I think we need to probably be clear on that. You cannot do everything in that list. It's got to be specific to your particular use case. And also the code of conduct, it does have elements. For instance, we mentioned software. Design or use energy efficient software. Well, what does that really mean in practice? Difficult to say, because we're not really measuring, certainly as an industry. I mean, you guys in research might be, but in the industry generally, we don't really measure the efficiency of software or the operating system, etc. So, and we should be, frankly, it's a real area of potential improvement. But we don't, and we don't really tell people how to do it because we don't really know. So before I finish up, there maybe will be questions, but before we finish up, the premise of this was talking about how we improve the code of conduct and introduce the AI element or the high density, let's call it HPC, high performance compute, high density compute, not necessarily AI. How we maybe provide a focus on that for within the code of conduct. And again, my challenge is almost back to all of you in this room. Tell us how to do it. You guys are at the leading edge of this. We just have to put it into practice. We have to make it work, which can be a challenge sometimes. And we don't always do it in the best possible way. So, we require people like yourselves to come to us and tell us what's the best practice. You may not have a solution. Again, like energy efficient software, how do we actually measure that? I don't know. If anybody does have that, please let me know. But you know, similarly with the hardware, similarly with the control, you know, John's holistic point, how can we actually bring the IT element and the building element together? Chateau and I were talking this morning in the car about, you know, we shouldn't be measuring necessarily individual components within the service. You know, let's bring the memory and the network element, the CPU element, the GPU element all together. You know, we need to look at the entire system. So again, to repeat, my challenge is to you. We will be doing an update of the code of conduct probably over the next 2 to 3 months or so. Unfortunately, the guy who leads it within the European Commission has been ill, so it has been delayed. But he's back at work now. Come to me with suggestions for inclusion. Come to me with, you know, once you've actually done that, really sort of, you know, that lonely night and read through it before falling asleep, and you see your evidence for improvement, let me know. You know, come to me, let me know. Come to me with new ideas, and you know, we can incorporate those new ideas and move the industry forward. It's a slow process. Like I said, we're still designing data centers for a peak PUE of about 1.6. So that shows you where you guys are and where we, who actually have to make these things work, where we are in terms of design. So there's a big gap. You know, help us maybe narrow that gap slightly. So my call is to you, help us improve it, help us move down the sort of the route of righteousness in terms of certainly high performance compute. Questions? Talk.
Which one is the best practice?
The best practice is the first. The first, which is communication. Stakeholder communication. One of the problems, one of the biggest problems I think we have in data centers is we are very, very silent. The IT guys don't talk to facilities guys. I mean, it gets worse, doesn't it? The network guys don't talk to the storage guys, don't talk to the, you know, the computer, the server guys. So I think the biggest challenge we have in data centers is lack of communication. We make a lot of assumptions in terms of dependency. So when we build a data center, again, we build a data center and we design to 1.6 because that's the worst case scenario. If we had certainty over the workload that was, or the platform or the workload that was coming in, then we could design a very different data center. You know, the analogy I use is like trying to design an aeroplane. You don't know how far it's going to go. You don't know how many passengers it's got. How many engines do you want? You know, so what we do is we do something very generic, which is not the most efficient. It can't be. Never will be. So if we can have a degree of certainty over what is coming, then we can be much more efficient. But to do that, we need to have far more effective communication between the different stakeholders in the group. So it's the first practice in the code of conduct, and it's the most important. And it's people. It's got nothing to do with technology. It's people, and it always is.
Let's take the questions at the end because we are half an hour late. But I want to just say one, if that's okay.
Sure.
Like I think the point was really relevant. I also, from my feeling, there are multiple European initiatives and projects which actually trying to drive us to the right direction, but basically sometimes we duplicate the effort. So I think from now, like we will have chance to comment, ask questions, but Mark here and other speakers now, we will leave the stage to Gemma and the Raul. Like, let's also try to make some comments on it, especially when it comes to like what kind of mediums that we can use, we can come together, join the efforts to drive us into the right direction. So OCP, John, you will mention it, Raul will mention it, like there are some organizations which can actually help us collaborate this effort and help also organizations and initiatives like the EU Code of Conduct, data centers and so on, grow faster to the direction that we want to go. Is it fair to say?
Perfect, yeah.
Okay.
Perfect. Good.
Okay.
Thank you.
Thank you.
So I'm not doing a very good job at keeping time, but so we do have Gemma. Is it Gemma next online? Yeah. Gemma Hughes from Alpha Lavine, from waste to value. Hello, Gemma. Can you hear us? Anybody out there?
Yeah, we are allowing the microphone.
Okay, right, yeah.
Yeah, we are working on it, Gemma. Just give me.
No,
You
now you can try.
can you try?
It's the people, not the technology.
Yeah.
Always.
Always, yeah. Can you hear us, Gemma? Yeah.
Yeah, we are a group of IT experts. Please help. Wait a bit. I can hear you. Okay.
So Gemma can hear us, but
But she can unmute herself. This is
Should be able now.
okay.
technology.
We are given.
Already did it. Yes, no.
I think we need to make a presenter.
Presenter.
Okay.
And change. And now she's a presenter.
Wait, can you hear me? Not muted.
She's muted.
How?
About on her side.
Wait a second. I will try something. Make a presenter. Change. Raul, can you unmute yourself?
Yeah, I think I can.
Okay, so it works. Gemma, since it worked for Raul, probably we granted you the exactly the same authority to present. Can you try one more time? Otherwise, I have to go for with my best solution. You can turn it off and on again, like the Teams. It works.
Shall we swap round?
Yes, yes.
Yeah.
We are waiting for you. Maybe we can shift to Raul. We can change the time of the presentation until Gemma comes in, if that's okay for everyone.
So Raul, are you? Have we got Raul's? Well, Raul will share
I
his
think that I
screen.
am ready.
Sure. Yeah.
Give me just a second. Let me prepare my slide deck.
Oh, I think also Gemma is back.
I'm good
Well,
now. Hi.
Yeah,
let's
we
go
hear you
with her
now.
then.
Okay, Gemma. Yeah.
The
Can you
turning
hear
it
us?
off and on again was definitely the way forward. Love a good IT
okay,
fix. It's great.
I'm brilliant.
That's all an IT guy will ever tell you. Just switch it on and switch it back on. Okay.
Okay, then is it okay, Raul, if we keep on with Gemma as we planned?
Absolutely. Go ahead, please.
Okay, thank you.
So Gemma,
Okay.
can you share your slide? I guess
Yeah.
you need-
I'm just going to make sure that you can see it rather than all my notes as well at the same time, which is always a good start. So let's
share
have a
the
bit.
right screen, yeah.
Can we see? Yeah?
Yeah.
We see it.
Great.
Oh,
yeah.
good.
All good?
Thanks a lot, Gemma. Yeah.
Okay, perfect.
So over to you. Yeah. Speak a bit louder as well. I think it's a little
Speak a bit louder. That's not normally a problem for me, John. I'm not normally told to be louder. I'm normally quieter, I think, in the general scheme of things.
This time you can be as loud as you like.
Okay, perfect. You can turn me down locally if you need to. So I just want to say hello to everyone. My name is Gemma Reeves. I work for Alpha Laval. I can put my camera on and say hello. Hi, everyone.
Hey.
Don't know if you can see me or not.
We see you. Hey.
Hi. Perfect. So I'm really sorry that I can't be with you guys today in Luleå. I had some other commitments came in, and it's nice to see a room full of people. I hope you'll find the event useful across the day. What I'm going to talk to you about today is heat transfer and a little bit about efficiencies and different applications for waste heat. I've heard some of the other presentations so far. I'll try not to duplicate too much, but we'll see what happens. So I work for Alpha Laval. So Alpha Laval is the global leader in heat transfer. There is only one slide on Alpha Laval. I promise it's only one corporate slide, but I just wanted to give you a feel for if you weren't aware of who we were, who we are and how long we've been around for. So Alpha Laval have been around since 1883, and we are an innovation-based company that continually develop and push the leads and where we are in terms of technology. And our core track technology is heat transfer, which in the data center world, as you've already been hearing about this morning, is extremely important. Enough of the corporate stuff. So when I was asked to present today, I wasn't entirely sure what direction to take. There's a lot of really good speakers today. I'm going to try not to duplicate, but really we're talking about energy and energy demand. And in the rise of AI, I know Mark was just talking about colo versus cloud versus AI type rollouts, and they will all change, and there'll be a market and there'll be a demand for all of these different types of demand basis moving forward. But I'm going to focus on AI during this conversation because this is what the topic of mine was. So what you can see here is a report from the IEA from April 2025. And if we just take a look just at the base case for the moment here, what you're looking at is a total install capacity of DCs reaching 225 gigawatts in 2030. That includes some cooling efficiency improvements, reaching about 1,000 terawatt hours in 2030. And that would then represent about 3% of total global energy consumption. That's a huge number. But what does it mean when we're talking about heat? Every kilowatt of compute becomes a kilowatt of heat. And as Mark was just saying, there's lots of different ways you can take that heat out, and how we take that heat becomes a basis for how we move forward with heat recovery or heat reuse. When we look at the numbers for compute, you're looking at about 40 to 50% approximately of cooling representing the facility energy use. It does vary by region, but that heat would have traditionally always been rejected into the air. What we're seeing with some of the new technologies that have been mentioned already, things like direct-to-chip and immersion, is that it's being rejected to liquid. And that's where we have a real opportunity to recover heat and turn it into a valuable resource. This heat recovery, and I'm sure Raoul will mention it as well, will support things like carbon neutrality, ESG goals. And where we're at the moment is a turning point. We're looking at operators, we're dealing with operators who are looking to find efficient, scalable, cost-effective solutions for recovering this heat and making it a viable thermal property. So I've just put a couple of images up there. I'm assuming everyone in the room has maybe seen a DTC system, a direct-to-chip at the top, and you have an immersion-based system at the bottom. These are the two main technology bases we're seeing at the moment being rolled out for the new AI generation GPUs and servers. So you're looking at direct-to-chip, where you have a heat sink, an immersion, and a fluid running through the heat sink, and then you have immersion where the servers are immersed in a dielectric fluid. Both of these are currently on the market and are being widely tested. But the key thing when we look at the heat transfer is the thermal efficiency of recovering the heat from air to the liquid, like I've mentioned already. Liquid is approximately 3,000 times more efficient to recover heat from than air. It's just easier. And where it becomes easier, it becomes more economical and more practical to then deploy, and you can get a higher quality of heat that you're recovering to then onward use. The technology for heat transfer isn't a barrier. This type of technology has been around for a really long time. And what we're doing now is trying to tweak it and flex it to make it work for these varying loads that Mark was talking about, for example, for finding the best way to capture the most efficient solution with the closest approaches to recover the most heat to enable you to then reuse it for other systems. And when we look at these types of systems, when we look particularly at the direct-to-chip and the immersion, it enables a higher temperature of heat reuse. I don't know if that's been mentioned already so far, but these temperatures, and I know John might disagree with me, but at the moment, these temperatures can be run slightly higher than a traditional crack-based system, for example. And those higher temperatures make a viable, more contact viable of heat. And I'll talk a bit more about what those efficiency means later in the presentation. So how does a company support these sort of things? Alfa Laval sit in many different places across the whole value chain. We sit in the white space, in brazed heat exchangers in CDUs, and we sit in the extraction. I don't like to call it waste heat because I only think it's waste if you're throwing it away. I prefer to call it heat management. Maybe it's a pro, maybe it's a con, I don't know. But to me, it's about looking at how you manage the heat that you're trying to take out. Are you going to throw it away and waste it? Are you going to recover it? Are you going to repurpose it? How can it really be used into another area? And efficient heat transfer really is a big, crucial part of that equation. And there are lots of different things that can affect how efficient the heat transfer of these types of systems are. And I'm not going to go through every single point that you have on that slide there, but I just want to give you a feel for some of the different things that when we look at a selection for a heat exchanger, these are the sort of things we look at. We look at how close the temperatures are between the circuits. We look at the delta T that you're trying to lose and gain from both of the circuits. We look at the flow rates. We look at available pressure drop and head on the pumps if they're existing pumps. So when you look at a retrofit versus a new build design for heat recovery, there are different things that you need to take into consideration. Efficient heat transfer is the core to all of these technologies, be it from the rejection of the heat in the white space all the way through and out to the heat recovery in the grey space or the wider world. As you move forward, the things that used to hold back heat transfer, if you look at a traditional shell and tube situation, just don't exist in this new plate technology. And that's for anyone's plate heat exchangers, don't get me wrong, it's not just Alfa Laval's, but plate technology is inherently more efficient than shell and tube. With a shell and tube, for example, for those of you that are familiar with that technology, you would be able to achieve maybe a 5, maybe a 10-degree approach if you want to keep the size of the unit down. With a gasketed heat exchanger, you can achieve a 1-degree temperature difference between your heat rejection circuit and your heat recovery circuit, which then provides a much more efficient onward heat to wherever you're going to do with it, whether it might be district heating, whether it might be any of the other applications. And that's across lots of different units. It's across the larger gasketed units that you might have outside the space, and it's also between the more copper braze units. So it literally sits at every single point. If you lose 5 degrees, for example, from your servers to your facilities cooling, to your TCS loop, that's quite a big gap of heat you're losing. Every degree that you can recover makes a big difference to the efficiency of your overall system. So when we look at heat recovery, what are we really looking at? Are we looking at being a value stream, or are we looking at being good for the community? I'd like it to just be good for the community, but in different parts of the world, that would also be part of a value stream potentially for a data center. And this is a really big question that we're seeing come up a lot when we talk to data center companies at the moment. Who owns that infrastructure? Is it owned by the data center themselves? Is it owned by the district heating company? Is it owned by, for example, whoever's going to be using it? Be it, I think, a greenhouse was mentioned earlier, I heard. And that's a big, I would say, barrier in some cases to how this heat is recovered, is making sure those conversations are happening early enough that you have a good plan in place to be able to roll this type of system out. I've seen a lot of different ways of doing that so far in the market because it's still quite new. We've seen a lot of instances where it's a profit share scheme. So initially that cost of the infrastructure is shared between the two parties. I've seen where the data center pays for it outright because they want to maintain control of their cooling loop, and effectively this is linking into their cooling loop. And then I've seen it done the other way as well, where pipes are just run to the border of the sites and the district heating company, for example, would put in that infrastructure. There is no right and wrong way of doing this at the moment, but the way you approach it and early engagement can make a real difference to how effective it is totally overall. What does also need to be taken into consideration is the total cost of ownership. If you are rejecting your heat, you're effectively getting free cooling. And I know, obviously, from a data center perspective, you can never design to assume that you're going to lose your heat in that way, but it can provide a real benefit. For example, how often you need to run your chillers, if you're getting that additional free cooling option through there. So overall, it will be reducing overall energy consumption and therefore lowering the operational cooling costs. It should lower emissions by reducing the need for cooling and the additional heating sources in the wider grid. And in some places, obviously, as Mark has already mentioned, we need to be careful of like the EU Code of Conduct in places like Germany, for example, where they have very strict mandates on having to make waste heat available for other opportunities within the wider system. And what I'm just going to show you now is a slide that shows you, and this was worked on with the Net Zero Innovation Hub, and this just shows you some of the different potential options for waste heat. Because in the Nordics, you're very lucky. There is a lot of district heating. It's not necessarily the same in lots of other parts of the world. So we need to look at alternative options. It could be district heating, but there are plenty of other things that can be considered. We've mentioned absorption chillers. They're being continually developed and driven to run at lower temperatures. I saw a solution the other day that's designed to run with a 45-degree inlet temperature, which historically absorption chilling would be looking at 100 degrees, give or take. So these companies are moving towards making their solutions more data center friendly to deal with some of the more newer technologies in terms of liquid cooling heat recovery. I think we talked a bit about drying of biofuels earlier as well, and wood pellets. We're seeing fish farming and aquaculture being done. We're also seeing opportunities where greenhouse companies are pairing with data centers to take the heat from them. There's a lot of different ways of approaching it. It's how much of a stable heat host you want to pair with as to how flexible that demand becomes and how stable it becomes from a data center perspective. But when we look at this, effectively, a lot of the time we are still going to have to include and consider heat pumps. At the moment, at least. If you look at the traditional district heating systems, you're looking at 60, 70 degrees. So there's going to need to be some sort of lift when you look at it. But the coefficient of the heat pump is directly affected by the amount of lift that the heat pump has to achieve. So the bigger the lift in temperature, the lower the coefficient of the heat pump. If you look at air source heat pumps, for example, and water source heat pumps, if you use those sorts of ones, you're going to result in lower coefficients of performance. The higher the waste heat temperature that we can reclaim from the data center, so the more efficient the heat transfer is in removing that temperature, the higher the heat pump coefficient of performance, and therefore the lower electricity use that you can achieve. We ran some numbers and we believe that from a heat source to heat demand, every 1 degree approximate lift reduction that is required is about a 2% energy efficiency increase, which is really very big when energy is such a challenge in the market right now. So I kind of want to leave people thinking of data centers. Data centers will always be data centers, and data centers are so important for the way we're living our lives and the way our lives are developing. I think everyone touches AI in some way, shape or form. My 8-year-old has AI on her computer at school for her learning. My 13-year-old uses it probably for gaming more than anything else, granted, but it's influencing every part of our lives. But we also need to look a bit bigger. We need to look at energy centers as data centers as potentially any energy hubs and sources, where some of this new AI-ready infrastructure, the direct-to-chip, the immersion, provides the opportunity to recover heat more effectively and efficiently. And then waste heat becomes a resource, and it becomes not a waste, but it becomes a challenge. It becomes an opportunity to do something with it. Heat transfer technology plays a really central role in enabling this shift, because the more efficient the heat transfer, the better the heat quality you can get out at the end of your system. And that's me done. 2 time as well, I believe.
No.
No.
Yeah.
Gemma, we were muted, so you got a round of applause if you didn't hear it.
Thanks, John.
But I guess, do you want us carry on, or do we should take some questions now? Because maybe we just take 1 or 2 questions now.
You are the boss.
I'm the boss. Okay. Or we're out of control if I'm the boss. Okay. So any questions for Jen? Okay, you've blown them all away, Jen, but I guess what you've actually said is the theme of what's going on today, and that's the temperature. We keep coming back to the temperature, and I know you said that with liquid cooling temperatures. When I first started working in liquid cooling 15 years ago, the only use case for liquid cooling then is said it was a waste of research because nobody's going to actually do it. The only benefit of it is actually the temperature you get out, and I think we're back talking about that today. But the problem we have is that, yes, I think there's some good research from ASHRAE and OCP and some other showing that temperatures, even when we use liquid, are going down. So this is the biggest problem we have. You know, do we want to run our systems hotter, and what are the consequences of that? And it goes back to a point that I made, which is combined heat and compute, or combined compute and heat. You know, which is more important, heat or compute? You know, should the compute be the waste product of the heat generation, rather than the heat being the waste of the compute generation? This is something that is interesting today. I think it's a theme for today's meeting, isn't it, really?
Yeah.
But what's your view then on, and you mentioned the word approach temperature. But your approach temperature was actually from the point of view of what we get from the IT to the point of heat rejection.
Yeah.
Whereas a lot of it depends whether you're looking at heating or cooling, because we're moving energy, whether we're cooling. So data centers are always talking about cooling. And I know people in this industry say we shouldn't be using the word cooling, we should be using heat recovery, not cooling. So a lot of the industry talks about an approach temperature, which is supply to the CDU, and then the temperature to the actual microprocessors. So why do you use an approach temperature? Your approach temperature is different to what the cooling guys are talking about. And that's where we can get ourselves into a little bit of trouble, because we're not talking about the same thing, are we?
In some ways, yes, and in some ways, no. I suppose if you just look from a thermal transfer point of view, I'm interested in the difference between the temperatures you want to run your TCS loop at, or on your, say, direct-to-chip system, for example, and then the temperature on the other side of that circuit on your facilities loop. I don't care if it's heating or cooling, really. I'm going to go heat management rather than heating or anything else. I think heat management is a bit all-encompassing. I don't care if it's cooling or heating or whatever you're trying to do, but the closer you can keep those temperatures, the more flexible it provides whatever you want to do on the other circuit. If you're just worried about the cooling side of it, it enables more free cooling for longer hours. If you're worried about the heat recovery or the heat reuse, it gives you a higher quality of heat. So I think wherever the temperatures end up on some of the newer cooling, on the new chips, wherever that guidance finishes, the new technology that's coming in with the DTC systems, with the immersion systems, it provides an opportunity, because it's easier to move the heat from a liquid to a liquid than it is from air to a liquid. It still provides opportunities to recover or reject that heat more efficiently and effectively.
I mean, as you say, 1 Kelvin approach on evidence. I mean, there is a capex side of this. You know, the bigger the heat exchanger, the lower the approach, and that's a cost for data centers. You know, but I think, you know, we should be focusing on that, and that's one of the things that is very important, to maintaining that temperature from chip to the point of heat rejection, which I think is what HEATWISE is all about as well, isn't it? I know you've got a lot more to it but if we just focus on the infrastructure, it's about getting the heat from the microsystems to the point of use.
I would say that this big vision is divided into multiple like calls, and there are also some upcoming ones. Like some of them are focusing on this aspect clearly, and you know, energy reuse on the AI systems, even like that much focused. They call it AI HPC, like as Mark also pointed out. So this was my point previously. Like these are all the things which are considered under multiple of different calls. They are prioritized by EU. Maybe final you know, close up can be like maybe getting Gemma's like opinion about the EU's position about these technologies, but I will come to that. So what I want to say, like we really need to be aligned under different public funding initiatives, because we need to go to the same direction. HEATWISE is only one of them, like obviously, and there are more that we need to merge, and we need to be stronger. This is important.
Okay. Yeah. Well,
I think having consistent messaging is really important. I think there's a lot of mixed messaging out in the market in general at the moment. And I think, like you've just said, I think it'd be really important to try and bring these initiatives a bit more aligned. Would be helpful for the data center companies, for district heating companies, for investors, for whoever's looking at it. Because it's not a CapEx question, really, it's an OpEx question. Obviously, you need to consider both, but it needs to be looked at completely holistically in the whole scheme of things. Yes, your heat exchanger might be a bit more expensive, but you can regain that because you can not run your chillers for 3 days a year, or you can, it soon sort of balances out a lot more quickly than you might expect going for those closer approaches and moving forward. But the way the EU have approached it, I think, is really interesting in general. I think there are 2 ways you can do it. I always say it's a bit of, you can go carrot or you can go stick. And I think there needs to be a little bit more carrot or a little bit more stick even in some situations. I think maybe there could be an additional thought around benefits for data centers if they can show they're doing this, maybe some tax incentives or breaks. Maybe there should be a tax on if you don't do it. There are so many different ways you could approach it depending on the country you're in. But I think we just need to think a bit more. To me, it's a little bit too loose at the moment. There's not enough guidance. I think it just needs to be a little, not crazy dictatorial, but a step towards a little bit easier to work your way through.
Okay, that's a good point. Yeah, I mean, we need to be talking about the same thing. I think this is one of the issues in this industry. There's a lot of the terminology is not well, and we should be using standards. Mark's point to that too.
Totally.
Stress the ISO, or if you don't like ISO, you can go EN, European Standards Country.
EN references the ISO.
Yeah, of course. Yeah, this is it. So EN references the ISO. Well, thanks, Gemma. Thanks for. Hopefully, you will stay on, and we do have a panel discussion, which I think is going to be a little bit focusing on some of the points you've raised as well. So,
okay, I'll stay on for as long as I can.
Okay.
Yeah.
Great. Okay. So we're going to move over. Thanks again to Gemma. Please, round of applause, everyone. Now you can hear it. Yeah. Now you can hear them. We're going to move over to Raul now. Who's on the line, calling in Barcelona. Are you in Barcelona?
I am here, guys.
Yeah.
Hello, everyone.
Oh, there you are. Yes.
And thank you. Here I am. Hello, guys. So first of all, thank you, John. Thank you, Chagatai, for having me here, to invite me here in to this conference. Let me start sharing my deck, by the way. Give me just a second, please.
First slide will introduce who you are, just in case.
Yeah.
So you can see the logo on his shirt. He's with the
exactly. You can see the logo there. Give me just a second. I have a bit of a technical. There you go. Technical challenges there, but fixed now.
You know what to do in the worst case.
It's not the technology, it's the people.
It is the people. So I'm really honored to be here speaking with you. Thank you, John. Thank you, Chagatai. I'm very happy to see very familiar faces here with Mark, with Gemma. I am Raúl Álvarez. I am the European Market Development Manager for the Open Compute project. And I prepared a bit of a slide deck of what it's actually, well, what it's OCP, first of all. I'm going to spend a little bit more time than Gemma on let's say, corporate discussion, mostly because it's interesting for what it's coming. And then I will give you a bit of an overview of what it's coming from OCP and in the data center design space, and how all of that connects to very European, let's say, led initiatives coming from energy management and liquid cooling. But let me start first with OCP. The Open Compute project is an international community. We are a community of more than 7,000 participants, which is mostly coming from, it's hyperscale centric. So all of the innovation is coming from the hyperscale, but it's affecting the rest of and impacting the rest of the market. Our tenets, as you can see here, are openness, sustainability, impact, scale, and efficiency. And all of the innovation that is happening there is open, is actually released in the form of specification. So specifications, best practices, and the goal of OCP is to open the market and to make innovation very quick to adopt in that sense, but at the same time being able to have discussions around future technologies that will impact the market in 3 to 5 years. And I will mention John and Gemma very soon about that topic. So we grew significantly from 2011, where we were established as part of an initiative coming from Facebook at that time. And right now, as I mentioned, more than 550 members. lots of people joining us in our summits. And the most important thing is that the impact that we're having in the market of, and even more so now with AI solutions and very high density solutions, where OCP is the base of all of those, all of that equipment in the industry right now. As you can see, this is just a sample of the companies participating, of our, let's say, company members. And you can see here from startups to cloud companies working with us. But at the same time, the most important part and the most relevant part of OCP is how we interface, how we interact with the rest of the industry through alliances, right? And we can see here, of course, RISE, but we can see AshRai, we can see Current OS and Net Zero, which they will be mentioned throughout this presentation. So, as I was mentioning, OCP is a community and it's a collaboratively community effort. So you can see here from our incubator initiatives like the Future Technology Symposium, where John is chair, and for instance, Gemma is sitting at the sustainability committee, up to emerging markets, but passing through all of our community projects, where the most relevant for this discussion will be cooling environments, data center facility. But at the same time, I'm going to discuss about our umbrella initiatives like the Open Systems for AI, Open Data Center for AI, and Open Cluster Designs for AI. So the way those initiatives work is they incorporate all of the work that is happening in the projects under a specific topic and a specific theme, and we will dive deeper on Open Data Center for AI very soon. But one of the most interesting initiatives coming from, regarding Open Data Center for AI is, of course, power distribution, even if we're not going to dive deeper on power distribution this time, because we are going to focus on liquid cooling. The goal of the community projects work, the goal of the initiatives and so on is to be able to impact the market, and this is why we have recognition programs, so product recognition programs and facility and security recognition programs, which allow any company to put products on the marketplace. But this is not the focus of this deck right now. So the way we work is very simple. We work through contributions, and contributions could be specifications, reference designs, white papers, and so on. We are organized in top-level projects, so projects and work streams, now with strategic initiatives on top. And the product, all of that work, all of those companies involved in that discussion are hitting the market through what we call contributions and specifications. Most of the time, people think about OCP as setting standards, but we are not a standards-based community. What we do is we create contributions, and then companies and associations, they can work with those contributions so they can become standards. Let me discuss, and let me go straight to the discussion about data centers and about Open Data Center for AI. So you can see here the three strategic OCP domains that we are looking at. So coming from AI, high density data centers, where of course we go from hyperscale, but up to colo providers and the rest of the discussion, not only about the facility design, but how we enable power cogeneration, how we enable power distribution, efficient power distribution with DC power, up to cloud DCs, and what we just announced, what we call the AI computing continuum. So how we follow the path of AI coming from the hyperscale to the edge and telco points of presence. And this is what I mentioned before. So the vision of the open data center ecosystem is very simple. Is how we align those strategic domains with our vision coming from grid to chip. And by the way, this grid to chip message is something that you can see. It's very pervasive right now in the industry. When we see big companies that potentially they impact the market with this kind of holistic vision coming from the understanding data centers as a full factory or a full building, where everything is very closely coupled. So let me discuss with you about the Open Systems for AI umbrella initiative very quick. This is very simple. We are getting together discussions about IT infrastructure, physical infrastructure, and grid interface. So coming back from what we were mentioning before, from grid to chip, the other way around, you can see here, and how we can let's say integrate those discussions when it comes to designing AI clusters. In that sense, how that set of machines that are working together as a cluster are being designed, built, and integrated into a data center, and then how all of those requirements are actually impacting what we call open data center for AI. So how we go further than the holistic IT and white space vision up to the data center and facility and grid as well. And this is what I just mentioned. So how we go from understanding this kind of machines sitting on the data center floor, and how we enable and how design power, cooling, mechanical, and management, and the grid interface. So all of the systems are actually running, and they are very closely coupled with the rest of the facility. It goes the same way. So the process is always the same. All of the work that we do in the strategic initiatives are going to impact, first of all, the market through designs and guidelines. So the expected contributions coming from the Open Cluster Design for AI strategic initiatives, and actually all of the strategic initiatives are going to be designs and guidelines. And I'm going to discuss some of them, mostly coming from the data center, the Open Data Center for AI initiative very soon. But then I want to focus first on the topic of this discussion, right? So how we enable liquid cooling. So we are focusing here, as Mark mentioned, we are focusing here on HPC type of designs, very high dense type of designs, where in that work that we have coming from the Open Data Center for AI, right now we have a specification, which is a base specification coming from the hyperscale. But when we try to understand the market, and again, I mean, no liquid cooling system is 100% efficient, as we mentioned. So there's always, when we mention liquid cooling systems, there's always the understanding that we are mentioning that those systems are inherently hybrid, where we need to enable some sort of air cooling for residual heat rejection, right? But the trend is clear in the market, as you can see here. And the trend is that as densities are increasing and chips are getting hotter and hotter, and that TDP coming from the chips, coming from the accelerators, and those machines is actually getting higher, we really understand that liquid cooling is is not an option. It is not an option anymore for this kind of machines again, but it's a requirement. And that discussion coming from the first, let's say, base specification that we have regarding Open Data Center for AI is actually very clear. But I wanted to first of all put you in context on how the industry and how we see the industry evolving and the different discussions that are happening in our community and the different projects and sub-projects, right? So as I was mentioning before, how we track the rack densities, right? How the rack densities have evolved in a very short amount of time, again, for this kind of machines, and how all of that is actually impacting the rest of the considerations from the white space to the facility. So 250 kilowatts up to 1 megawatt, and even, well, we see this in the future evolving as well. But the industry right now and the hyperscale industry is actually working on the pretense that that the 1 megawatt rack is going to be a reality, and how all of that is actually impacting power, but in this case, cooling. How we enable cooling for this kind of equipment, how we design the cooling circuits, how we design CDUs, but then how we design the mechanical infrastructure for that. So rack manifolds, operations in this kind of equipment, and then how we design those data centers to be nimble as well. And I think that the industry as a whole right now, when we look at this kind of machines, are converging. The industry is converging through a single trend, as we see here. So what we are seeing at OCP is that direct-to-chip liquid cooling is actually growing in not only market size but in demand. And one of the great contributions coming from the Open Data Center for AI is a standardization around the mechanical design and the CDU design, where you can see examples coming from Google, where they standardized the whole aisle with end-of-the-row CDU. And by the way, these kind of designs, they are not new. You can see the HPC market working that has worked on those designs, and those are production designs coming from companies like HPE and Cray, where they have the same kind of design. But right now, what we can say coming from OCP is that there's a work about releasing specifications that start to work on the design of modern and open and data centers that are actually following this trend. I was mentioning end-of-row CDU, and you know, in that context of open data centers for AI, again, we recently had a contribution coming from Google about the design of the end-of-row CDU. And this is a great example to understand how these kind of open contributions are actually impacting the market. So these pictures that you see here on your left are coming from our past global summit, the show floor. You can see a couple of brands there. You can see Boyd and MVCool. But the way this kind of specification has impacted the market is that right now we have on our marketplace, I think that right now more than 7 vendors that are producing equipment based on that specification, which is called the shoots. So it's a great way to understand how OCP is impacting the market, and it's impacting the market for this, let's say, very specific type of data centers coming from the liquid cooling side of things. Then, just to give you an overall context on the discussion of the fungible data center, I want to discuss with you how this is being done in this strategic initiative called Open Data Centers for AI, where we need to, again, make different considerations coming about a data center facility, right? So how we allow different energy sources, how we allow distribution voltages and different cooling temperatures and power interfaces, different layouts, and so on. And not only that, but how we understand the facility as in a holistic way, and how we allow different form factors moving forward, right? So when we understand that Open Rack version 3 has been more or less the de facto standard coming from this kind of machines. Right now, we are seeing other vendors that are working with OCP, and they are releasing specifications for a different type of rack. And all of that needs to be considered in that way for when we understand the vision of the fungible data center. So again, I want to show you, and this is, by the way, I'm going to share this with you after the call. This is part of the specification, the base specification on the Open Data Center for AI, where we are laying the foundation of small scale data center designs, right? So when we understand this kind of double row facilities that by themselves, they are extremely dense. In this case, I think that this use case is used for Google TPUs. But those designs can be easily adapted for different kind of workloads and different kind of machines. When we look at AI, for instance, and the great thing is that right now, that base specification is encompassing all of that kind of design, and it's readily available for the community and for the rest of the industry to catch up on and to contribute on top of that. And this is an example. And by the way, this is not only in a drawing. So if you've been attending, for instance, NVIDIA GTC, if you've been in any data center world, we were the other day in Data Center World London, you can start to see examples of this kind of infrastructure designs already being presented to the rest of the market. So even if this is coming from hyperscalers, the work that they are doing is with the rest of the ecosystem, and all of those designs have been validated as well. So you can see here that we are seeing a very important part of the cross section dedicated to power delivery, but at the same time, we can see dedicated liquid cooling zones, let's say tightly integrated into the design as well. And this is just an example, again, coming from that open data center for AI specification that we have as a proposal coming from Google. And you can see that the designs that I was showing before, if you see the data halls, you can see them right there on the number one. I'm sorry that this is, let's say, sideways. It was the only way to fit it on a single slide and being properly visible. But you can see computing, you can see mechanical on 2, 5, and you can see loading bay area 7, 3 and 4 as well, and 6. So right now we are looking at a design of a proposed design for a very dense data center, which is fully contributed to OCP and the community. But then it comes the real challenge, and it comes the real challenge here in Europe, where the US is catching up on. And this is the perfect opportunity right now to step up And by the way, I want to mention that when we look back at the projects and the sub-projects, there's a very important work being done by, as I was mentioning before, by the Cooling Environments project and the heat reuse project, where we can see, Gemma working there, but at the same time, I want to mention Jaime Comella, I want to mention Peter Terenius, where the way they work is has a profound impact on industry alliances, right? So when we look at ASRAI, when we look at the Net Zero Innovation Hub as well, this is something that we work in collaboration with them. But first of all, I want to mention really quickly, as Mark was mentioning about the EU Code of Conduct and the taxonomy here. There's been a bit of work happening on carbon disclosure as well, coming from a collaboration from the iNations Climate Accord, and I wanted to highlight this quickly as a way to showcase the work on sustainability that we are doing under the Open Compute project, where we have not only a sustainability project, but sustainability is considered in many other projects where they have dedicated sub-projects or work streams, let's say, discussing on sustainability. And this is, by the way, it's a very simple framework, right? It's a framework that doesn't mandate a specific calculation methodology, but it's focused on how we do standardized disclosure. So the way is to make this easy for the industry, but at the same time do it in a standardized way and try to address inconsistent reporting and overhead, which makes this kind of reporting cumbersome most of the time. This is just an example, and by the way, this is very simple, as you can see, on how we should do or how it's proposed to do a disclosure for a fictional UPS system. So we have different sections for the different considerations coming from the respondent, from the product methodology, and the embodied carbon reporting here. So very simple, very easy to do. And again, I mean, why we need to adopt this, or why the industry should adopt this kind of reporting, that, by the way, it's actually very simple and it's open, and it's a specification, not only a framework that we collaborated with iNations, but as what most of the OCP community is doing, it's fully open for inspection, and it's right there in our website. So again, what I was mentioning before, very simple. Streamlined reporting, being able to have a good baseline to be able to compare the data, and to be transparent, and to support the industry targets. There's a bit of a call to action to adopt this, which is interesting. But again, this is another opportunity to collaborate and to align with the rest of the industry. But then I want to go back to heat reuse here. And by the way, most of the work that most of the material that you will see here is either work coming from our collaborations with other industries, other organizations like the Net Zero Innovation Hub, which we are working with them very closely on heat reuse. And you can see a good example of the reference designs. This is just a schematic. There's actually a reference designs for heat reuse specification done by the project, which is available as a contribution that you can go to the website and check. But I just wanted to give a bit of an overview. And by the way, Gemma, just jump away if you see anything that you don't like or you want to comment on. I would really appreciate the help. Again, reference designs coming from that collaboration with the Net Zero Innovation Hub happening there. As we were mentioning before, I think that I was just playfully indicating that in the chat before. The heat reuse project has a strong alignment on policy and regulation, which is not only coming from European regulations like the EU Code of Conduct, where we are actually looking very closely, and the team there is looking very closely at the overall EU Code of Conduct, but in regards of waste heat, physical layout, and heat reuse, they're looking at the right metrics that are proposed. And by the way, I'm very happy to have Mark here because we can have a sensible discussion afterwards. But there's a strong alignment, and there are many opportunities as well on the alignment of heat reuse on that design that we were discussing before about the open data center for AI design. And I don't want to finish without mentioning the collaboration that we have through EUDCA, through the Net Zero Innovation Hub, where we are working with EuroHeat and the European Data Center Association on enabling a platform to understand how heat reuse is available in different regions, but in different markets as well. And this is a great collaboration that it's happening, and it's showcasing the work alongside other organizations and the strong collaboration that OCP is working with. So I'm going to start now. I'm going to finish now here and do a call to action on everything that I discussed before. There's a tremendous opportunity right now happening in our community to try to align the heat reuse and sustainability aspects of data center design with the open data center for AI design. So what I want to mention here is I want to do a call to action for you to join the different forums there. If you have the opportunity to do so, to drive and to run those initiatives and those discussions and those projects. And of course, I mean, OCP is thriving on alliances and collaboration. So we are right now working with RISE. We are working with others as well to be able to have, let's say, aligned contributions coming from those organizations as well. And as well, I want to mention, and I'm going to just do a bit of a let's say focus on that one on the importance and the relevance of attending OCP calls, OCP webinars, workshops, and come to the summits where this discussion, the discussion that is happening in the community, is happening face to face, and it's discussed face to face. It's a great opportunity to meet with the community and to have face to face discussions about the different topics that not only we saw here, but are being discussed in the different projects. With that, I want to do a couple of calls to actions and participation. There's a regional community. There's different regional communities projects happening in OCP. I wanted to focus on the European one, where we are tailoring the discussion to what is going on in the European region about the data center market. So you can go there, you can scan the QR code and join the project. We are running calls every second Tuesday of the month. And there's interesting discussions about heat reuse, about liquid cooling, which are mostly the main topics being discussed there because they are very important topics happening in Europe. And of course, I don't want to forget about doing a call to action for you to come and join us in Barcelona very, very soon, by the end of April. Again, scan the QR code here to know more about the EMEA Summit, which this year is being celebrated in Barcelona very soon. So with that, I want to thank you all. And I think that we can open the floor for a question or two regarding what we just presented.
Thanks, Raul. We're running way over time, but we might have time for one question.
I'm thinking about this. Thank you for the presentation, HEATWISE. But I'm thinking about you talked about the products that are marketed and have that kind of a flow into open compute. But how are the products, a single CU, for example, verified that it works? And the second question, when you're going to operate it in a data center, you build the data center, how are you going to deploy it? How do you know it works? How do you test and verify it in the open computing?
So the way, and by the way, thank you for the question. This is a very interesting one.
It's a loaded question.
It is a loaded question, I know. That's okay. The way we validate, the way we run product recognition is actually very simple. So as we have a contribution already in the contributions database, anybody that wants to apply to have a product, let's say, validated by and passing the validation mark, so you can say that that product is OCP verified or accepted or inspired. The way we do this validation is through the different projects and sub-projects that have worked and contributed that contribution, right? So for certain projects, there's going to be a discussion about the product-based specification, and we will match how the product matches the initial specification. That means that what OCP doesn't do is active testing. We don't have testing facilities branded by OCP. We collaborate, for instance, like with RISE here with John and Chadai, where some of the testing is actually done, but it's not defining the OCP product recognition. The product recognition that we issue is regarding the specifications. So I hope that this answers your question.
I think Tor heard what you wanted to hear. Yeah, is that we do the testing.
I want to hear that they have a program, a call to action to start testing the equipment according to the spec at RISE.
Okay, yeah, you didn't quite answer the question.
Thank you for that.
But anyway, thanks a lot, Raul. A round of applause again. We're going to have to move on. So we're going to take a 5-minute quick coffee break, and then we're moving one of the presentations that was before lunch, after lunch. I forget which one that was.
Yeah, it is like at HEATWISE overview and
yeah. So if we can move this after lunch, so we can have the fun of connecting women, and then this panel discussion, which we will try and do a little bit shorter, for lunch.
Yeah. Can I just say something? Yeah, like it's like a friendly environment here. Probably we have to squeeze the coffee breaks and luncheon. But this is the beauty of it. Like we're gonna sit down together and we're gonna actually discuss when we are having the sandwich and coffee with you together. So please use this opportunity to interact. Let's discuss. Like the lunch break and the coffee breaks, we should use really good to benefit from it. And if I may take one more second, because since everybody is also here, I want to remind something. OCP is an open community where where actually sustainable digitalization is flourishing. And I think it had one of the biggest impacts on the sustainable digitalization. Why I wanted to say that, it is really important for you to understand that in this open community, we co-create the future, right? You can, you don't have to be like having a title or something under OCP. The meetings are open, and the recordings are published, and everything is being built in an open mindset. So one last thing, Raul is leading the European side, but I'm a bit proud of one thing. In OCP, for example, last global summit, there were around, I think, 11,000 people. And when you go there, you feel the energy, like you feel the energy of the people, except two communities, OCP, European community, and Cooling community, because we are being jet lagged so much. Like I see that there is a big impact of the European market on the sustainable digitalization, especially about heat recovery and the cooling sides. And I think more or less all the initiatives that we do and the challenging European regulations that we are facing, whatever won't kill you makes you stronger. I think we have to see it from the brightest side and use it as an advantage, because once we go through it, I think we will be even stronger and we will drive the ecosystem even more. Yeah, just one final takeaway. I couldn't stop myself. I had to say it.
There's a shout out for OCP there.
Yeah.
Shout out. Yeah. Thanks, Rob. We're going to take a 5-minute break for coffee, and then we'll proceed with the women in. Is that just you, Tina, or you've got comments? Okay, so you're going to take a few minutes to say a bit about that, and then we have a quick panel discussion, which we can bring in the sandwiches with the panel discussion if you want.
That's what I was thinking too. I didn't want to push it forward.
No, as long as they can speak, they haven't got a sandwich in their mouth.
Yeah.
Okay, 5-minute break. Thanks a lot.
Yeah, thank you.
Okay, I guess that we can hear me also online. So yeah, hi everyone. I'm Tina Stark from RISE, but I will now sort of give a short introduction to our quite newly started initiative, Women in the Data Center Industry. We're a part now of SweDCI, so the Swedish Data Center Industry Association, which we're very happy about. So if you go to the next slide. I've got to start a little bit with a background and show you some data. So from UNESCO, we see that only 1 out of 3 researchers globally is a woman, and just 35% of STEM graduates are women. And women hold only 22% of STEM jobs in the G20 countries, and only 1 out of 10 STEM leaders is a woman. So closing the gender gap isn't just about equity, it's about unlocking innovation and building a stronger future for our industry. Yes. So seeing that women then remain significantly underrepresented and the data center industry is rapidly growing, we thought that there's an opportunity here to strengthen diversity and attract more female talent. So sort of our main questions is sort of how can we encourage more women to join and strengthen the position of women already established in the industry. So this is the core group that started this initiative. So it's Anna and Amanda from Conapto, me, Parvati, and Annie from RISE. Our vision is to create an inclusive and empowering community that connects and inspires women in the data center industry. Doing this by fostering knowledge sharing, collaboration, and supporting increased representation across the sector. Our mission is to reach women in the industry through, for example, SweDCI, partners, or other existing industry networks. We want to establish a forum for ongoing contacts, meetups, networks, but also showcase the data center industry to young women and future women in the data center industry, and also connect with international communities of women in tech. But who is this community for then? Yes, of course, women, but women working in any part of the data center ecosystem, and not only exclusive for women. We think that also for industry ambassadors and senior professionals who can uplift this initiative and then also, as mentioned, current and future students in tech education. We have some planned activities now for our first year. And now in the first spring, or in the first quarter in spring, we will have a members meeting. We will have also a webinar and a meetup in Stockholm together with IMAs and women. If we look then more to the fall, we will have 2 more members meeting, a networking event, and hopefully a young women outreach where we connect with future students. But our most recent event, or our upcoming event, is our first members meeting. This will be held on the 14th of April at 3:30. And please sign up as a member here on our website Women DCI, where you then, if you become a member, you will get the invitation link for this meeting and upcoming meetings and other information that we will send out.
So I can be a member.
Yes, everyone can be.
Thanks.
So thank you so much for listening, and yeah, please follow us, either become a member and follow us on LinkedIn. And I think building an inclusive and innovative industry is a shared responsibility among all of us. Thank you.
Thank you very much, Gina. So you want to, hopefully everybody clicked the QR code.
We didn't have time.
Oh, put it back up. Yeah, put it back up, yeah. In fact, leave it up because we're going to move over to, unless there's a slide for the panel. Is there a slide for the panel?
No.
No slide for the panel. So let's leave the QR code. So we're going to move on to a panel discussion about sustainability.
Oh, that's QR code, the member.
That one, yeah. Okay. So I need, can we get some chairs up here?
Yeah.
Do you want to, so we've got 4 panelists, none of them are women, sorry. Well, at least join us. At least, Tina.
You're showing his work through that.
So if I could welcome to the stage Rasmus, Mark, Frederick, please, yeah, and Torbjörn.
Can we have the nice chair?
Certainly. The boss is there.
All sit in a comfortable chair.
Yeah.
So, do we have them on camera? Yeah.
Yeah.
So, just remind me, what was the title of this? So, you know, in other words, sustainability.
I'm glad you're on top of it, John.
Any question, anytime.
Any question, anytime, yeah. Panel discussion, the future of doing sustainability. Well, that's a big word, isn't it? So, we didn't meet to discuss this. So this is all completely organic. They have no idea what I'm going to ask them. But I did a quick check of who I've got on the panel. So, and I thought it would be good to have an icon for each of the panelists. So forgive me for doing this to you, but Rasmus, you are the academic here. So do you want to just say where you're from? Because maybe people online haven't seen you.
Yeah, thank you. My name is Rasmus Jensen. I'm an associate professor from Luleå University, Department of the Built Environment, working with energy efficient buildings, HVAC systems, indoor environment, and so on.
Okay, and then to Frederick, who I've iconized as the engineer. Yeah. So we got the academic, the engineer. Yeah. So, but you're saying
left.
I'm worried.
I'm really getting worried.
So I guess I introduced myself before, so with Luleå Energy and with district heating and cooling of the Luleå city.
So, and then we got Mark here, who I've identified as the consultant.
Yeah, the so-called expert, yeah.
The so-called expert.
Thanks, John. Yeah, I do run my own consultancy. I am a machine engineer as well, so I've got a foot in each camp.
And lastly, I've identified him as Torbjörn as the researcher, yeah, although he might.
Okay, so Torbjörn is my name, head of the RISE research team in data center.
So we got the shovel, we've got the thermometer, we've got the metrics guy, and we've got the grid guy, yeah. So those are the icons. So we're going to be talking about sustainability. I guess you can hear me without the mic, but let's use the mic.
Not
So,
online.
not online, yeah, maybe they can't. Yeah, I don't know how far I'm away from the mic. So we're moving to, from these low density racks to high density racks in AI data centers. The question remains is, this isn't an incremental change that we're seeing. In some respects, it's a massive change. It's a total re-imaging of the infrastructure, as has been pointed out a little bit. Now we're moving into the realms of liquid cooling, a subject that I've loved for many years, and now is a little bit more useful than it was 15 years ago, because everybody wants a piece of the action when it comes to liquid cooling. So we talked about temperatures a lot, and I thought what might be a good way to start is to ask you to say whether you think we should be focusing on the heat recovery in this, or should we be focusing on doing something better with the IT? So, I don't know who wants to start this, but maybe Tor, you might have something to say. I know you're very vocal. So.
Yes, I think the software guys, we need to push a little bit there on that bottom. And there is initiatives out there. So I think European Code of Conduct could include research already done, looking at compilers, looking at languages, looking at things like that. And the thing is that now with this vibe coding, it's going to get worse. Because what's going on is that time to market is the key thing for the software developers. So if the code is efficient or not, that's not important. The first step is to get to the market with a really good software solution. And with vibe coding, they will increase the speed and have less control of the end result, how efficient it is. So yeah, that needs to be included in the code of conduct, how to optimize the code, get good advice, use these compilers, use this language, do this with the vibe coding, do this. Yeah.
Absolutely, my high hopes.
Good. No, I completely agree, Tor. I think, one of the big areas for improvement is definitely on the software side. You talk about vibe coding, but, people are using Python, which is one of the most inefficient languages out there. To your point, it's speed to market. It's not about efficiency. And I think going sort of back slightly, I think one of the things we're guilty of in our sector is focusing on PUE. Now, we talked about PUE earlier. So it's a useful metric, but I think it masks problems in other areas. It masks problems in the IT side. It masks problems in the software side. We focus on the cooling and the delivery of energy to the IT, but I don't think we're doing enough on the IT side. Should we be looking at heat reuse? Yes, of course we should, but let's not just focus on what we can do with the building. Let's focus on what we can do with the IT.
SUE.
Yeah, exactly. Yeah.
SUE.
Yeah, SUE. Yes.
SUE.
SUE. I haven't been that bad. But then, talking about sustainability, I think we also need to factor in, the scope 3 side, the reuse of equipment, what we're doing in terms of, the raw materials and the use of what goes into both the building and the IT platforms themselves. So there are so many different facets to sustainability. And if you really want to go into the weeds, then the social aspects, maybe less use of what I call frivolous AI, or actually that's actually what Nest coined. The use of these amazingly powerful products and platforms for just, cat videos or whatever it is. And it's ridiculous use of what is a very, very powerful function that is consuming energy and resource. Should we be really doing that? Probably not. So.
But Frederick, you do need the heat, as you were talking about. What is your appetite to bring data centers into the fold?
No, since we have a long history of basically using energy from other sources, and let's call it waste energy, it's that's what we want to do. That's a rational thing to do, not just for our business, but also for society in general. And taking a bit of a bigger perspective, so looking at district heating in Sweden in general, we are lucky up here. We have really affordable district heating, but looking at the rest of the country, it's been a very large challenge last few years because many of them would based district heating on biomass, which has been really expensive, and of course has another lot of other uses that could be better. So in many other grids, data centers could be even more interesting to put into good use. And of course, there are a lot of data centers being built in Sweden. So to take that opportunity, of course, and I think it's also pressure on data center developers to make that happen. But of course, this is once again the challenge of temperatures. Basically, how can we meet? But that's definitely
temperature is an issue.
can play a big role.
Yeah. I mean, in terms of the building, Rasmus, I mean, what are we, I mean, I know that HEATWISE is integrating IT into a building in this project, but I mean, when we build standard buildings for other purposes, should we always consider IT infrastructure as being part of that?
I'll try not to spoil too much of my talk later today.
You're going to tell us more about it later, yeah.
But I think we actually all have an obligation to try to minimize energy use, maximize, you could say, waste heat, reuse. I think Gemma had a very important point in terms of carrot or stick, in the sense also that I think if there are no incentives, right? You talk about we should do more about the source code. The code should be more efficient. So yes, we should do that tomorrow when we get more time. We should design better building. We should renovate and so on tomorrow when we get better time. But if there are a financial incentive, people move extremely fast, right? So I think preparing all industries that produces or emits heat to be able to collect that and use it if ever applicable, to design and adjust and upgrade all our buildings to be able to integrate excess heat at, you could say, as many different temperature level as possible, actually, right? As flexible as possible. I think we all sort of have an obligation to bend towards each other to try to actually make this work. Because if you look sort of at climate change and all of these things, right? This is actually one of fairly low-hanging fruits. So why not do that? And I think that the driver for this, it might be different in data centers. You are the experts, but within buildings, the driver is legislation. We have a few front runners that really does a lot of good things, but 95% of buildings, they follow minimum requirements or barely follow minimum requirements. But can we tweak something? It could be taxes, could be whatever, so that you actually earn money by doing what is, you could say, the right things in terms of reusing. I think that would be where we should aim for. And then, of course, you need someone to find out where should we go actually, right? And how should we do it.
So, I mean, this project has been talking about its energy reuse factor. I mean, you have a target for this the HEATWISE project. You know, that's and that is a standard. There's a standard associated with that. Mark, you mentioned PUE going through a second version or maybe a third version. I'm not sure, but has it actually addressed the issues of, for example, if you are supplying heat to a heat network and the heat network upgrades the heat for the district heating, right, and gives cooling back. You know, the original PUE was saying if you were purchasing cooling from a network, you had to factor that into your PUE because you're not doing the cooling yourself, but you're purchasing the cooling, so your PUE should factor that in. But if you're actually supplying heat to a heat network and you're getting cooling back, has the PUE factored that in yet?
There's a big debate in this because it's something that is not necessarily within the data center operator's control. So the challenge is, why are you penalizing a data center operator if they offer heat and nobody wants it? It's relatively easy if you've got a district heating system next door that actually needs heat. But in many parts of the world, and certainly in sort of, Western Europe, Southwestern Europe, we don't want the heat. Nobody wants it. I mean, that's the fact. And so you can advertise that you've got several megawatts of heat available, but what do you actually do with it? If there's no district heating system built, if there's, you know, nobody wants to do greenhouse, or, yeah, there are so many things you could in theory do it. But the other challenge is that to get that to work, to get the heat reuse to work properly, you need to have a joined up planning process. You need, you know, if you're planning a data center, what you need to be doing is offering that waste heat to other industrial or residential processes that can take advantage of that heat. But the problem is that's not the way we work. You know, it goes back to what we were saying earlier about human communication. You know, if we were able to actually communicate more effectively and actually look at the potential benefits that we can bring to each other, then we'd be much better at doing this. Yes, it is a free resource in effect, but we're just not very, very good at taking advantage of those free resources, whether it's data centers or other heat producing industrial operations. So back to your question about PUE though, yes, there's been this big debate about whether the heat reuse should ameliorate the PUE. My personal view is that it shouldn't. I think it overcomplicates it because in the same standard series, we've actually got energy reuse factor, ERF. So we already have a metric for measuring the amount of heat that we're reusing, the energy we're reusing. And the problem is, if you take individual KPIs and you bring them together, you can get some very, very strange and incorrect incentives produced. So if you think about PUE and WUE, so WUE is water usage effectiveness. The challenge you've got with water is that it's actually really, evaporating water is a really good, cheap way of cooling. Now, if you're doing that in the Arizona desert, where you're depleting an aquifer that takes 1,000 years to recover, then that's a pretty bad thing, you know, obviously from a sustainability element. But if you're doing it in, let's say, northern Scotland or Ireland, where actually, you know, it kind of comes down from the sky, it's free, so why not use it? So, you know, it's water reuse is not necessarily, water use is not necessarily a bad thing, but you can improve your PUE by using water. So what should we focus on? Should we focus on water or energy? So you, again, by combining these things, and people try and do this on a regular basis, you see all of social media all the time, oh, let's take this KPI, add this KPI and this KPI and multiply it by this one. Then we're going to have this fantastic metric, aren't we, for energy efficiency? No, you're not. You're just going to have something stupid, which is meaningless. So I'm actually against, and I know that the new version of PUE has sort of factored this in, but I'm actually against it. Okay. And there's a move to actually create a European version of PUE, which doesn't have this in. So EU, EU, yeah, I know, don't get me started. But it's not simple. On the one level, intuitively, you think it's energy and we should be managing energy, but actually, I think we're in danger of creating perverse incentives for ourselves.
Yeah, and I think the guys that are actually, you know, invested in reusing heat, so they have an ERF that might be 90%. They take a hit on the PUE, particularly if they're using heat pumps in their data center, because you follow the PUE to the ISO. Yeah, it's in the boundary, and you have to factor that in. But you're actually putting in energy to upgrade the heat for the network. Yeah. But you're not getting compensated for that in the PUE.
I know, but you look at something like direct liquid cooling, and we saw, you know, Raoul put up his sort of designs for the CDUs that are doing, you know, sort of high density liquid cooling. Did anybody notice the pumps in those? Yeah. Okay. So those pumps, you can have 35 kilowatt pump in those things. And there are two, because it's redundant. Yeah. Where does it sit? It's in the white space, isn't it? Yeah. So you know that people are going to factor that into the IT energy consumption.
So it's the CDU in the white space is in the IT. Yeah. CDU in the grey space is.
That's facility, isn't it? Yeah. So PUE is a little bit of a game, which is why you shouldn't absolutely not look at PUE and talk about it in terms of energy efficiency. It's not. It's measuring the overhead the building imposes on the delivery of energy to the IT systems. That's why it's effectiveness, not efficiency in an end. So just be very careful. So I've taken too long, John. Sorry.
Yeah, no, but Rasmus, so you wanted to add something to that, please.
Yeah, because I think you're probably in data centers facing, could say, some similarities to what we have seen in the building industry. If you look back at buildings, let's say 100 years Buildings look very different around the world because they were built for local climate.
Yeah.
And utilizing as little energy as possible. And then when we see the last, I don't know, 20 years, 30 years, 40 years, buildings all around the world, they look the same, right?
Yep.
So very inefficient, but built according to the same standards. So what we are trying to do in the building sector now is trying to be a bit more holistic. So we do, you could say, sustainability assessments, right? So you try to look at sort of everything, and of course you can't look at everything, but you try to cover as much as possible that is relevant for buildings, and try to make, you could say, one score where you could be penalized for using too much energy, have too bad indoor environment, actually use too much money because then you can't build something else, and all of these things. And if you do that, and your calculations is locally based, then in Scotland would not be a problem utilizing water because it's not a scarce resource, right? Whereas in Arizona, it would be a huge problem. But running it on PVs might be a good idea, whereas in Scotland, less good of an idea. Right?
Exactly.
So I think one of the solutions to some of this is try to look at sort of everything of how your industry is sort of impacting the global environment, and try to factor in as many, you could say, inputs as possible to have the local context being an important part of calculating your KPIs. Because if we just use the same KPIs all over the world, all data centers would look the same, and it's not a real smart way to do it.
We're getting the debate going now, so Tor.
Yes, and that is really fire me up. Because now there is a drive, and it is driven by the big hyperscalers, that it should be no difference to run a data center in Spain and in Sweden. They try to normalize the PV even. So take away the local bad environment to run a data center, just to kind of saying, okay, it's if we have a sustainable data center in Spain, it's the same as a sustainable data center in Sweden, but it's not. So that is really a bad move right now, and it's pushed by the big scale guys because they have the same data center everywhere, not locally optimized. So they want it, get it normalized.
Dare I say, in many cases, though, those, the big boys, the hyperscalers, they're being criticised because of their lack of adherence to ESG protocols and whatever. So I think they're playing a bit of a game in terms of trying to show themselves in a good light. So they have numbers and make them look good. Whether that's actually truly representative of what's happening on the ground is highly debatable. So I agree. But the localization I agree with. I mean, actually, I won't say you heard.
And don't mention the IT.
Don't mention the war. No. No. In terms of localization, though, interesting. We're actually working currently on a version of the EU Code of Conduct for Africa. So we're trying to take some of the best practices and put them into more of an African environment. But that's a real big challenge because obviously Africa is such a huge continent with so many different environments. So we're nevertheless trying to do something with it, which exactly goes to your point.
Can I comment something?
Yes, I'll watch it.
A bit of a different perspective. I used to work at Stegra, the steel plant being built in Boden, not too far away from here, and I was involved in the waste heat topics. And I think what really sort of sank into me was that, okay, so this is a huge project, and you could compare it to maybe a really big data center. You have sort of a project where the main focus is sort of your process or your industry. So in that case, due to steel, in data centers, it's still the sort of the compute part that's the key part here. So then enforcing on those kind of projects to also manage all the waste heat management and all those topics, that sort of brings an already complicated project into a very complicated project that can sort of deter the project or maybe cancel it in the worst of cases. So I think this is a challenge more for also where do you draw the line? Where's the takeover point? And I think what we landed in at the steel plant was that, okay, so we can't think about the district heating and all that and all those implications, But basically, here are two pipes with lukewarm water. Do whatever you want with it. But we can't manage that. So put that maybe challenge onto the sort of the takeover part of the industry, so maybe the district heater provider that, okay, what can we do with this? Okay, we add a heat pump here, but we do it and not the state data center or the industry. So I think that's all of, because don't require maybe data centers to do too much of the heat management because that's not their expertise.
Correct.
And they don't know really how it has to integrate it into the district heating system. So I think that's also where sort of our industry could do more. Just be preparing for whatever sources there could be.
Yeah, that does bring some other challenges, because I think there are some examples of data centers that are connected to district heating networks, and the district heating network is upgrading the heat, but they say we only want to take your heat between the months of this part of the world, between the months of September and May, and in the other 3 months you're on your own, guys, and we can't help you. Yeah. So how do they? And I know it factors in that. How do you deal with that kind of situation?
Now that's a good point. And coming back to the steel plant, of course, from the industry side, it's cooling, whereas from my side, it's heating. But that steel plant want to be autonomous when it comes to cooling. So no matter the time of year, they want to make sure that they can cool things. And then that even gives less interest into supplying waste heat to someone because they already have the cooling. Of course, it could be more symbiotic while with the heating company supplying the cooling to the industry and be more sort of closely connected. But most industries would to be independent or autonomous in terms of cooling. Because to your point, yes, we would like to heat maybe not all months of the year, but can we then provide the cooling for the data center, for instance, also in the summer? From the data center point of view, that would be more interesting, obviously. For the heating company, it would be a challenge to use that waste heat in the summer, but yeah, you could use it for absorption, chillers, or something like that.
Okay.
But it's a more symbiotic way. That's more challenges.
Makes sense. Yeah. Maybe providing as a service also, just so that the problem is shifted away from the data center to the district heating network.
Yeah, that is something we see that the big companies, they really would like to be disconnected. As little interaction as possible because it complicates things. So they try to look at new ways of doing heat reuse, but it's not very easy to find. They want to produce electricity or produce cooling or produce clean water or do something else inside their premises. No interaction, no interaction with outside. But that's hard. So there's no easy way of doing, no easy technology to find. But that's a call to action. Try to find new ways to do heat reuse, new technologies for heat reuse. That would be a really good challenge.
Yeah. So I think you're right. I think going back to the incentives, I think it's interesting. There are actually at the moment there are disincentives. It's actually quite difficult as a data center operator to offer your heat to somebody else, particularly if there's no ready-made off-taker. It's very, very difficult. And in some countries, including in Europe, if you are giving away energy, you become an energy producer and you're taxed. So, there are all sorts of disincentives. And I think, again, probably going back to the sort of planning idea, unless we're more joined up in the planning process in the early stages of planning, and there are, let's say, possibly incentives, but certainly removing any disincentives, we're just not going to do it. As a data center community, we're not going to do it. It's just too difficult and commercially not viable. So, I think there are some barriers at the moment. It's not technology. We can deal with the technology. Again, it's back to people and people planning policy. Sorry, Jim.
Yeah, so I really was going to go to that point about the heat that is taken from data centers, and we want to, the optics again. Yeah, is it a renewable source of energy? If it's come through the data center and now it's being reused, because this is something that we're playing with the terminology, renewable. It's all about energy at the end of the day, but
Well, it's only renewable if your primary energy source is renewable. isn't
Yeah,
it?
if your primary energy,
So, you know, and define your primary energy source. Is nuclear renewable? You can have a whole debate about that.
Yeah.
So, but I think, you know, it goes back to the point, doesn't it? If you're supplying heat from one source to another process, it's not that you're actually being renewable. It's just that you're preventing somebody else to have to use energy from that primary source. It's an offset. It's not really saving you any energy. It's not really, you know, the data center operator. There's no real benefit other than the fact that you're preventing someone else having to spend money on energy, or you're making it easier, reducing the overall impact, environmental impact.
yeah, unless you're getting the cooling back and you're not having to pay for that.
Yeah, sure.
Yeah.
I think that at least in Denmark, the country that I know best, we plan to have a fully renewable energy systems in like 10 years, 15 years. Let's say world is a little bit behind an average, so 20, 25 years. So this about being renewable is sort of an intermediate discussion that we have. At the point where sort of all our energy is not based on fossil fuels, but is renewable, what it comes down to is the amount of energy that we use, because it costs land to produce it, it costs resources to produce, and it removes, you could say, economy from other stuff.
Yeah.
But of course, we should focus on the CO2 emission now and reuse and so on. But I think in like a generation from now, it will be a matter of, again, primarily looking at the energy use, how much energy is needed. Because we could put PVs on landfills. There's a huge debate in Denmark about that coming up for the general election. But we would like to have somewhere to live. We would like to have somewhere to go to nature. We would like to have somewhere to grow crops, so we have something to eat. We would like to have somewhere to grow our building materials so we can build houses. And we would like to have somewhere to produce energy. So resources and land will be a scarcity. And I think that in a generation from now will be sort of the driver for all of these. And we might as well start thinking about this now, so it doesn't come as a surprise as you could say the CO2 emissions did for us. Like, I don't know, we have known it for 50, 100 years, but seems to be surprising to us every year. Anyway.
Yeah, so I mean, a lot of the sustainability, I mean, I think the sustainability metrics, but they are focused on carbon, energy, and water. But one of the things that none of those metrics really consider is the actual material, the material resource. So I don't know any of you want to say anything about, you know, if we're trying to reuse heat, we're putting in more, maybe we're putting in more infrastructure. What should we be measuring if there is another metric that we should add to these myriad of metrics that takes us on that? Because we're a very energy and carbon myopic industry in that sense. You're all looking a bit blank, so maybe nobody wants to take it.
I mean, in the building industry, we do life cycle assessments, right?
Yeah, life cycle assessment.
Yeah, so we take all the materials into use, and you can have a very technical, fancy solution with a very efficient heat recovery unit for your ventilation system and so on, but uses a lot of material. So in principle, if you do the calculations detailedly enough, you would see, do we need to have a heat exchange efficiency of 80, 85, maybe going up to 90, or is 60 actually better? Yes, we will use more energy in operation, but we will use less material and less energy for producing it, right? So finding this balance, and that's also why I think there will be data centers where we should not try to reuse the heat, either because it's at a too low temperature, it's too energy and material high to sort of put it somewhere, or maybe because it's just placed too far away from any, you could say, industries or housing that can actually utilize it, right? Going back to your plan, I think we have many big data centers in Denmark. They are all built outside cities because land is cheap. They typically is put up where you have an electricity grid, good internet connections, and that means that almost none of them is connected to district heating, even though we have 65% of Denmark's heat by district heating, because it's easier, it's cheaper, and you don't have to worry about it.
It's true.
Yeah, I think I'm going to end with one last question to you all there. And it could be a little bit provocative, but I think we talked quite a bit about policy, standards, carrots, sticks, all that kind of thing. But if we could make one European regulation or technical standard tomorrow to help us towards this 1 megawatt rapid Raoul was talking about, and that we have talked about, what would it be? What would you want to change tomorrow going forward?
You want to start? I would like to take your suggestions. All the de-incentives, let's remove those.
Remove all de-incentives,
Yep.
yeah. So incentivize.
Yep.
Or have more incentives. Remove
I think we should start removing those that is sort of counterproductive.
Okay.
A big thing actually in the Swedish district heating business is to try to remove taxes on electricity use for instance, for heat pumps.
Yeah.
So that's and also for electrical boilers, because that would bring some flexibility into district heating systems towards the volatile electricity market. But yeah, so those are quite easy things.
Okay.
Yeah.
I mean, is that a country-specific thing? Because I know different countries operate.
Yeah, it depends on how you tax the electricity usage, basically.
Yeah.
But that's I know that's a big topic for data centers.
Yeah.
Also, obviously, but specifically for the heat production.
Yeah.
If you can use cheaper electricity for heat pumps, you can use a lot more waste heat sources.
Yeah. It opens up the market a bit more. Yeah.
It's also challenging because we're a bit afraid of all private households going into heat pumps. So I'm thinking about ways we can limit that.
Yeah.
So there's actually a suggestion to remove the tax for district heating companies where you have the system benefit and not for households. But that's
a good option. Yeah.
It's a bit sensitive topic also. Political topic.
Yeah.
But that's one thing that would help waste heat usage.
Yeah. Back to our politician.
Yeah.
What do you think about it?
I think there's one thing, specifically talking about data centers, but if there's one thing I think we could do to improve energy efficiency and probably reduce energy consumption generally, I think it's actually a standard for IT energy efficiency, including the software.
Yeah.
Now, we've been trying to do this for about 25 years and nobody's done it yet. And again, I'm in a room full of academics, so I'm still going to throw the challenge out there. Unless we're measuring the efficiency with which the IT platform does its job, whatever that job may be, we're not really going to do anything around, energy efficiency in data centers, in my opinion. Now, I'm not saying that's easy because IT does lots of different jobs. It does it in different ways. And we need to factor in the network. We need to factor in the software. So it is not an easy challenge, but it's one thing we could do. It's give us a way to focus and measure on the way that energy is consumed by IT platforms.
It's a really difficult one.
Because you didn't say the easiest.
No,
you said it's difficult.
But is there a regulation that is there anything technically we can do that? That's interesting.
I agree with Mark. That is a low-hanging fruit, but it's really hard to pick. It's really stuck there. But and the thing is that if you let the software guys work alone, they will come up with something that they don't care about what's the infrastructure doing with their software. And if we as infrastructure guys are trying to do this, we don't care what's going on in there. So we need this need a collaboration between those that are in the software infrastructure part of it and those in the hardware infrastructure part. It's not cannot do it alone, each industry by itself.
Yeah, so we need to bust some silos, as well.
Yes, the bust the silos.
Bust the silos, yeah. Communicate.
Completely agree.
Yeah. Okay, well, it wasn't very difficult, that was it. But I don't know whether there's any questions in the room for our experts, the academic, the researcher, the consultant, and the engineer. Are there online? Oh, one question, yeah.
Can I read it? Because I'm combined with one question.
You read it, yeah.
Yeah. So the question is, cat videos or any kind of AI generated videos.
Yeah.
I actually wanted to read it because I heard about it and math nowadays.
Okay.
In one of the TV shows in Turkey, I heard that there are some claims that one AI prompt is using a half a liter of purified water, and we have to be so careful about it and so on. So, but this comment is actually, I will read it until the end. There are some fair points, so we should dig in a bit. Sure, it's not the greatest use of resources, but it is fair to blame the end user. When it is the hyperscalers or multinational companies pushing their AI services onto us with all their might. Is it time to us to start promoting fragile AI, interesting term, which I used in one of my recent cases. It's a really interesting point. And if so, who should be the end of the, who should be the one to enforce it? I want you to consider it this way, like AI, there are a lot of AI videos right now. There are a lot of conspiracies and so on. But do you think that about a handprint of the AI, how much of a carbon saving that it can lead us? Like, can you combine these two into each other? Like, okay.
Well, this is going to take us another half an hour.
So I have a pet theory. I'm going to say it anyway. Let's remember who creates the demand for these services. It's us. Yeah, we get people like Extinction Rebellion going to a data center in Benton Island. Every single one is got the phone up, streaming or taking pictures, forgetting the irony of what's happening there because they're creating demand in the data center, right? But I think it's almost rather than sort of saying who controls it. People don't understand. People. You talk about water. People think that data centers all use water and purified water. I mean, where did that come from? So insane. But I think the problem is that people do not understand the impact of what they're doing. And the analogy I'm going to use is if you go to a supermarket to get your lunch, get your sandwich, it has this measure on it, and it's called calories. Well, calories is energy, isn't it? Forgive my basic physics, but that's what it is. Calories is energy. People can fully understand what they are consuming in terms of energy into their bodies to understand maybe have less calories, more calories, and you can make a choice. That's the point. You can really blow it out as much as you want and feel probably very ill as a result, or you can moderate your input. It would be lovely to be able to understand as an individual consumer what our digital footprint is in terms of energy consumption. Wouldn't that be amazing? Because then, all the kids that are out there complaining about data centers will understand that they're actually part of the problem. So, an understanding of individuals' digital consumption or digital energy consumption, or energy something as a result of their digital activity, is I think probably the first step. And if you're not informed, you can't make a choice. It works well in the food industry. Why don't we have something similar for the digital sector?
Yeah, but that's because it has an immediate effect on us, the calorie intake. But I mean, who looks at the CO2 footprint of flights and makes a decision on that?
Every airline, because they want to charge you for it. They charge you an offset.
Yeah, they charge you for the offset, but I mean, who makes it? Yeah, you presented the information, but do people actually react?
But unless we have the information, we can't make it.
No, that's the first point. Yeah, first.
And that leads us into our proposal to one of the hyperscalers that had a open call. We proposed a project, remember, John?
Yeah.
That we wanted to do an analogy to the gigabyte of download content. Mm-hmm. So you get it would be scored also to the how you load the environment.
Yeah, sure.
So you have to pay more if you're going to do 64 gigabytes of content that is not good for the environment. So you have to pay. Mm. So then you also have an incentive to reduce. That was the idea, but the reviewer they didn't like it.
No.
We would reduce maybe the.
Yeah, they don't reduce consumption, do they?
So I'm not sure that would be the sole solution to sort of let the individual decide. I'm not saying that was what you intended to say. Within the building industry, we are trying or starting to look at sufficiency, right? So when is enough? A standard single-family house in Denmark in the 60s, that was like 120 square meters. Now it's at least 220 and growing. and it's probably 45% of the buildings, right? But 2 adults and 2 children is only 15% of the families. So we are building bigger and bigger, and we are living in families with fewer and fewer people. Why? Because we can afford it. And so at some point we need to have a discussion about how much are you actually allowed to use, both in buildings, but I think also in data centers and so on. It's an annoying conversation, and we can all agree that it's some of the others that are spending some of the resources in a not efficient way, so they should start first, and then we can come after. But I think this is a discussion that needs to be moved from sort of an individual basis. I like all the information and so on, but I think if just information about calorie was enough, then Novo Nordisk in Denmark would not be a very successful company. So those companies, they are very good at pushing their products to us, making us sort of addictive is probably a strong word, but I mean they have a lot of incentives for us to use their products, right? So there need to be some kind of regulation, some kind of control, some kind of setting. This is how much you can use at some point, because otherwise, if you look at human history, our consumption is just going up until you have a war or an energy crisis, then it drops down and then it goes up again, right? And this can not just go on. We need to do something different.
Yes, efficiency is a really good term that haven't really talked about in this industry. But then how do you enforce that? You know, if your battery is empty, you have to do something about it. You have to recharge it. If your fuel tank is empty, you have to do something about it. But how do you do that when you've got endless supply?
Yes.
You need an authoritarian government, don't you? To tell you what to do.
But ultimately, it's not endless supply, is it?
No.
It just appears to be.
It appears to be endless supply.
Yeah.
So we have.
No, I just want to remind you like about the endless supplies or sandwich supplies. Some people are helping themselves to benefit from the supplies. Can we just wrap that?
Oh no, you can. Why don't you just okay. On that note, yeah.
Cut the movie.
We got to get to the food. Okay. So no, that's fine. Yeah, I need to be reminded. I'm completely off. Anyway, but thanks to our panelists here, the 4 of them here, and we're going to enjoy lunch. So people online, what are we taking? 45 minutes. Back in 45 minutes.
Can we start at 15 maybe? It's 35
Yeah,
minutes.
1:15. Yeah, so we're bringing the sandwiches in. Yeah. Okay.
Yeah.
Sorry, short lunch, but.
Also, there are some online questions. If that's okay for everyone, we will collect them and we will revisit them.
Okay. Today or later?
Later today.
Later today. Okay. Yeah. So it keeps our people online connected.
Yeah, please, sure. But anyways, like we will also answer them in written if possible, so they can follow up if they don't have time.
Yeah. Not many.
Now they can hear you.
Now they can hear me. Okay, we're starting the proceeding. Right. So little bit of a shift on the timetable. We're running a bit late, but our next presentation is on the HEATWISE project, overview and technical vision from H1 Systems. I think, David, you have on presentation, and you have to tell him to change the slides.
Can you just look at me?
Yeah.
You go.
My name is Peter Shadows from the Eastern. I'm leading the VP9. That is
Sorry, I should have introduced you. You can sit in the chair.
So I will speak about something which is very much connected with HEATWISE, of course, and the previous presentation. And that was good to hear that what's happening in the large scale. But I have to tell you that the HEATWISE project is not concentrating in this high scale project, what we could hear earlier. We are on the, I think we are on the level that we can more feel in the normal life. Please give me the next slide. Originally, I planned this presentation structure, but I realized that it's much more, and all of the things what is mentioned here is mainly was in the previous presentation. That's why I would like to concentrate on only three things from this. So when somebody asks me, Tamás, what do you do this more detail? What about the HEATWISE? If they know that I'm working with that, always the big question is for me that, okay, what is the result of that? Because everybody can speak about a lot about the scientific things, but the normal people hardly can understand that. So that's why when I created this presentation, that was the main motivation for me to speak about these things, how the things working when we just speaking with each other about the small things. So let's see that. So this is the three topic. What are the expected results? Why should we believe this? Because that used to be sometimes a question. If we put some user number somewhere, and if they like it, how can we implement it? So I think this is the three categories which is very important. So let's go forward. And this is the answer for my brother, for everybody who asked me. So in the waste in the HEATWISE project, we will do huge amount of energy saving for the tertiary building, and we will have significant CO reduction, of course, and we would like to be compliant with the efficiency requirement. And we would like to do what will be the result. We would like to scale it up to the best level. So, and these are the main numbers what I can tell anybody. So we will have some 100, 300, and around 900k euro per year. That is the energy saving. And you can see the CO reduction, but you can ask me that, okay, these are just numbers. Why I am telling you 6 numbers at the beginning? And I can tell you there is no meaning at this moment. But if we go to the next slide, I can tell you the background. So when we see these numbers, we have to think about that, okay, if we do something which is connected with HEATWISE, it's always very important to see the climate conditions. Everybody know that if we have the same building in, for example, Spain and in the Scandinavian territory, that's behave any absolutely other way. And sometimes it means more heat, and in Spain, it's not need any other heat. So that is a big difference. Always we have to calculate where is the things. So, and the other is the energy prices. So when I show you the numbers about the savings, it's always that what about the pricing level and of course some technological things and the others. So that is very important to see what is in the background for the numbers. Let's go to the next one. So so when I put the numbers there, that is in my mind too. So everybody who have in decision, who have to do some decision about something, they would like to do 3 options. So if they have money or if they have some needs to do something, they would like to see exactly what could happen if they have small amount of money, larger amount of money, if they would like to have more savings or much more savings. So that's why we think that it is very good to have this 4 version of approach for the numbers and for this type of project what we are doing. So the first one is always that is a mirror to the guy who would like to do something with this building and with the energy what they have, and the construction and the IT part of the building what is in there. So and this is the version where they can see exactly what's happening in their site. And the second version and the third version and the fourth version let's show the way what we can do. The first version is then, okay, we checked what's happening in the data center and in their small data center. I forgot to tell you that the HEATWISE project is not concentrating on the big data centers. We are concentrating on the tertiary building, and if the tertiary building has a small amount of IT workload, we would like to do it inside the building. And if it's much more, then in that case, we can connect it to some other building. So this is the absolutely other side than you were talking earlier. So these are the main steps. And the last one is then how can we do the most effective way this heat the savings. So let's see the next page. So this is the first. You can see the picture. If we see a building, a tertiary building, it has 2 several territory. One is the server rooms and the other in the heating system. And what we heard in the previous presentation, who cares about the programming is not care about the infrastructure. And that is similar simulation in the tertiary building, that somebody has have to heat, never speak with the guy who has to operate some of the servers inside the building. So, and that is the normal view in Hungary. I made an example in the hospital configuration in Hungary. You can see the details of the hospital, and that's the first. That is the numbers. That is the mirror for the owner of the building. You can see there is no reduction. There is no saving. This is as it is. The PUE, this is the number what we can, this is not good, but this is the KPI what we have to mention always when we are speaking about some European demand. So that is PUE, ERF, PS, cooling, wastage. We can see that there is nothing happening at this stage. Let's go to the next one. But if we go a little bit further, we can, that is about the smallest investment of what the building owner can do. Just simply connect the server room with the heating system. And we can see that in this case, okay, we have a good news that we have the waste heat reuse. We can manage it, but we can see that the numbers is not too high. So we can see that is an easy project, but maybe it's not enough for someone. Everybody want to see that what could happen if we put more money into the system. You can see that it could be operational cost saving that is 100k euro per year, and the CO reduction can be visible, and the PU it could be a little bit more, and the ERF and the PS is starting to come into the picture, but it's not a huge level. So let's see the next stage, what could happen. So and this is a big transition, because in the previous presentation, we could hear that the turning to the steam into liquid is a big step for everybody who have dealing with the servers. But in that case, this could be the big step what they have to do. If we do this liquid cooling system, in that case, the temperature level, which is come from our server, will be maybe enough high. If we have a good, efficient building heating system, this temperature level could be good without using any type of heat pump. But we will have a presentation about that, we can see exactly what's happening inside the building. And we can see much better numbers here. You can see the PUE could be as low 1.1, that is very good level. But the ERF, you can see that it's starting to be high. But this is nothing enough, because the PES level, the primary energy saving, is a very important KPI to see the whole picture. But this is not speaking about just this part of the system, not just about the data center part, or it's about the full building. So when we see it as a full building, and in this case, it's a very good number. It started to be a very good number. And you can see the energy saving level is tripled down. So when we speak about a company operating, for example, a hospital, this number could be visible for them in that project. But okay, we have the appetite. Can we increase something? And that is the next page, what we can do. So when we have the better question is, how can we put more IT demand into the system? Because there is a hospital and they have some some equipment, for example, CT and the other very specific equipment for measuring the body and the other things. And that is a limit within the hospital. But if we connect and aggregate, we are doing some computing workload orchestration, we can have much more IT workload into the building. So that in that case, if we do this, we can size this type of the data center and the data center capacity as the maximum, which could be useful for heating the building. So that's, if we follow this, you can see that the PU will be the same because the technology is the same. The ERF is same for the data center, but the PS level could be very high. And that is, I think that the level that everybody could think about it. Let's see the next page. And it is the summary of this four-level approach. And that is the most important part that in my mind, that there is two types of orchestration which can we do. If we have a huge data center, we can orchestrate the heat to the building, and that's why we have the district heating system. But when we are speaking about a building, tertiary building, as it is, it's much better to create some edge computing site in these sites and use their heat and maximize their heat for reaching the highest level of the BOVs. Okay, and let's go to the next one. Okay, and this is the summary. You can follow the changes of the number. And I think this is the proposal we would like to put to the table of the stakeholders when we are speaking with them in the future. And that could be the result of the HEATWISE project for me. There is some other findings, but this is the most important part, because if somebody has to make decision, that is the first thing they would like to see. What is the failing? What is missing from here? That is the ROI, but I will come back with the ROI in the next symposium or when we will be next time. So let's go to the next slide, please. And if somebody is interested in the detail, you can check it offline. Let's go to the next one, please. Okay, and what is the scientific and technical foundation of these numbers, what I put in there? Because we can think that, okay, Tamás, you put this number here, that, okay, that is true, that is realistic. Yes, we have to validate these things. So the HEATWISE project is about to do this calculation, to do the modeling and measure it back. And after all, we have to convince everybody what the result was there is good for the future. And you can see that is one of the most important part of this. It's the high temperature waste heat availability. So we will have a presentation of it. Zutakon will have this presentation and show you what is the background of this type of liquid cooling. The building heat demand modeling is very, very important, because we have to connect the two systems to each other, and that will be the presentation again after me. And efficient evaluation framework, that will be another presentation. So you will hear the details, you will hear the data just after my presentation. Let's go to the next one. And that is the other thing. What will HEATWISE deliver? So first of all, as I told you, we have to give to the stakeholders exactly the value proposition, and we have to give them an investment logic, because this is not the normal logic that we are following when they do something. So that's why we have to show them the right way how to do it. And the next one is that if they have the decision, any of the stages to do, somebody needs to do it well. So we have huge amount of engineers, but they don't have enough experience doing this type of things. That's why we are creating the design pattern and the padding tools for them, for easy use. That will be much easier. And you could see that this orchestration and operating this type of buildings and model, it's a need for giving the information. How can you do it? So we have to give them the information and the good pattern how to do that. And that is one of the things is very important, the risk and constraints, because you can see that is other type of data center, other type of working. If there is a small, or maybe not small, if there is a hospital, and it will be a larger data center, so it is other type of operation, not as usual as the hospitals work earlier. So that's why it's very important. And the last one is just a feedback for the European Union that they have to change something. We heard in the previous presentation that somewhere when you have huge amount of heat and give it to somebody, you have to pay huge amount of tax. So that could be a problem. So we have to give them some feedback that how to handle this, how to ease this thing to happen. And the other is that we checking the standardization, that we have to change anything on the standardization to ease this process to happen. So thank you for your attention. And I would like to give the microphone to my colleagues to speak about details.
Okay, thank you. So who do we have next? It's unlocking the potential of heat, excess heat. This is one of our colleagues on online. Yeah. Luleå. Can she hear us?
1 second.
Okay. With you in 1 moment.
No.
Okay.
Okay, so hi everybody, let me just share the presentation.
Hello, Lila. Can you hear us here?
Yeah, can you hear me?
Yes, we can hear you very well. Yeah.
Okay,
Thank you.
excellent. So I'm trying just to share the presentation. Okay. Is it in the presentation mode?
Yeah.
Okay.
You're not in presentation mode yet. Can you put it in presentation? Sorry? You're not in presentation mode at the moment. Yeah, that might work. Yes, now you're here. Yeah.
Okay.
That's good.
Okay.
Thank you.
Okay, thank you. So hi everybody, my name is Lila Bushmitz. I'm a product director at Zutacorp. And today I'm going to talk about unlocking the potential of access to it. So Zutacorp has developed a unique technology based on a phase change from liquid, the electric liquid from vapor, then condensing the liquid back to vapor, and then condensing the vapor back to liquid, providing a very efficient cooling solution, enabling a very high thermal design support, cooling and power at any and power efficiency at any climate, as well as very efficient economic heat reuse. I think we've discussed it pretty in depth during the previous presentations. So I'm going to do it fast because I did prepare slides, so sorry about that. So it's getting hotter. As previously said, of course, chips are getting very powerful as the demand for AI is increasing faster and further due to the AI revolution. Also, during the GTC conference being held these days, it was said that chips processor are planned to be 2.3 kilowatt per processor and exceeding this. And the racks will be 400 kilowatt and even 600 kilowatt, meaning it's going to be a lot of heat to dissipate, since nearly 80% of the power is converted into heat. So most of the data centers, like I said before, I think also, are still being cooled by air. This will be challenging to support these very high power GPUs, and will cause consuming energy, increased cost and carbon footprint, especially in water usage and greenhouse gas emission. So it is clear that a new approach is needed. And liquid cooling, like also said before, is coming to fill up this gap, assuming to be more being able to handle these kinds of loads. So I think it was also mentioned before, but I will do it very quickly. So technologies, direct-to-chip liquid technologies are cold plates, can be cold plates with the liquid inside placed directly above the processor, or immersion, where the whole server is being immersed in a tank, like I think, John, you presented before. The main drawback of the immersion technology is that you have to have a completely different infrastructure for the data center. And also you need to have a complete material compatibility, since every part of the server is being touched by the liquid cooling, the electric liquid. The main drawback of the single phase cold plate is that the liquid inside it is water or a mixture of propylene glycol and water, meaning in case of leakage, the server can be damaged. Zutacorp is leverage the best of both worlds, because we take cold plates, but inside there is the electric liquid rather than water. This way, in case of leakage, no harm will be done to the server, and you don't need any infrastructure changes, as well any material compatibility, since the liquid is flowing inside a closed system. So how does it work? It's pretty similar to the way you boil water in a pot. The heat source is heating up the water inside the pot. Bubbles are being formed at the bottom of the pot, detach from the bottom, float up, turns into vapor, and remove the heat away. It works the same way in our system. the chip is getting hotter, heating up the liquid inside the cold plate. The liquid balls turn into vapor and remove the heat away from the chip. So if it's so simple, why won't everybody doing it? The problem is that is the hotspot. When the bubbles are being formed at the bottom of the pod, they form like an insulation, and the area underneath this hotspot is not being cooled. When you're dealing with water in a pot, it's not a problem. But when you're dealing with the chip, it means that the transistor placed underneath are not being cooled, and this may cause throttling. So to solve this challenge, Zoteco has developed a unique structure of fins and wicks, which prevents these bubbles from being formed at the bottom. You can see here on the left vertical positioned cold plate, and on the right horizontal position the cold plate. You can see, I think especially on the left, that no bubbles are being formed on the bottom. This is an opportunity to have a look inside the cold plate. So how does it work? The basic principle is to have a pool of liquid inside the cold plate at all time, keeping it cold at all time. So now the pool is filled with the liquid. When the dye starts to warm up, eating the liquid will start to boil. The level of the liquid will go down, the orifice will open, allowing for more liquid to enter the cold plate and keeping it at the same level, making sure everything is being cooled. The vapor turning, the liquid that turns into vapor will go out through this use tube and will remove the heat away from the chip. On the system level, this is how it looks. This is the cold plate, like you saw before. We have a CDU heat rejection unit functioning as a condenser and distributor at the bottom of the rack. So liquid is being distributed through the manifold to the server into the cold plate, boil, turn into vapor. The vapor is being collected back by the manifold into the heat rejection unit, turns condensed back to liquid, and go up to the servers again. This is how it works. You can see here that we have different products. It's the same principle, of course, but for each chip, we need a different cold plate to be specifically designed according to the layout of the processor. Here, this is the server loop for the new NVIDIA servers, a different kind of CDUs and manifolds. So, like you saw, two-phase direct liquid cooling has advantages at all the levels: data center level, the system on rack level, and on the chip level. On the data center level, it allows a reduction in the capex since you need a lot less chillers. Also, OPEX is being reduced because you don't need all the maintenance you need when you use water, for instance. And you improve your efficiency, enabling a very efficient heat reuse. On the system rack level, you can densify the rack. You pose no risk to the IT, and also you gain energy efficiency. On the chip level, you can support a very high CPU and GPU power. And also, since the principle is about pool boiling, so the cooling is occurring instantly. And also you get a uniform cooling since the heat is going upwards and not above the die. So there is no flow of liquid above the CPU rather than the heat is going upwards.
Yeah, you have to start again with the slide, yeah.
The beginning of the slide? Okay, so I'm saying that on the left you can see data center being cooled by air, and on the right data center, the same data center being cooled by Zoteco. And you can see the difference. You can see the space saving, since you need a lot less equipment, also the capex saving for the same reason. And also because you can densify the racks, like I said before. You can gain energy saving, less water consumption, and heat reuse options. I will talk about this a little bit in the next slide. I don't, oh, okay. So using Butacore, you can elevate the temperature of the liquid that you're using, and also the facility water will be, you will be able to have a higher temperature of facility water. This will enable HEATWISE opportunities such as, like I said before, in other presentations, like district heating, industrial heat process such as distillation plants, industrial drying process, agriculture implementation like greenhouse or fish farms or algae farms. And also you can use the energy for the data center itself, for instance, to warm up the offices at the data center, and also hot water supply. So with data cooling, you can dissipate it through a phase change, which is more efficient heat, which allows for more efficient heat dissipation, rapid heat removal while maintaining stable temperatures, higher rack density, reduced power usage, and reduced environmental impact. We actually turn it into value. That's it. Thank you.
To the mic.
Yeah. So do we, can you hear me?
Yeah, I can hear you. Can you hear me?
Okay, yeah. Yes, we can. Yeah.
Okay.
Any questions from the audience? I think most people know your system, but I guess you had a slide on advantages. My question would be, what are the disadvantages of Butacore? Or the solution? Rather, we not name the company, but name the approach, the cooling approach. Would you say there are disadvantages on two-phase cooling? I know you're using pool boiling.
Well, I will not be perfect, but now let me.
Sorry, I put you on the spot. Yeah. Maybe there are no.
That's a good question. Well, I think it was also said before. So, I think for not very high, loads of racks, I don't think you should put, you should change your cooling system to our system, because it does include. I know it doesn't require a different infrastructure, but it requires investment that I'm not sure will be worthwhile for 10 kilowatt racks or something like that.
Okay. Yeah.
I think I would go with air. I would stay, but I think the main advantage is if you want to actually gradually upgrade your data center, and you don't want to go through a full, new infrastructure. I think this is a very good solution to have like, 1 or 2 racks for AI, for instance, and you can use our system allowing, like a modular growth.
Yeah. But on the heat reuse, do we have any figures yet on the temperature of heat recovery from the system? Because your system is deployed. I think we have it in RISE, don't we?
Yeah, this is exactly. Yeah, this is exactly the kind of test that you are doing right now to determine the limitation, I guess. But yeah, we do have to comply with the NVIDIA, requirements of the temperature, which is challenging. But I believe from both ends, like the district, I think before it was said that district heating will design systems to be able to receive lower temperatures of water, and we will have to, I think it will, together it's going to be a win-win solution.
Thank you. Yeah. Okay. Any questions from the audience here? No, I think we're going to move on. Thank you for presenting today, joining us from far away. I don't know where you are actually, but thank you for joining me. Okay.
Thank you. I was planning to come, but it was not possible.
There are some challenges. Yeah. We have a lot of challenges, don't we?
Yeah, but we are overcoming it. Like with the heat, we're going to make it.
Thank you very much.
Source. Thank you.
Okay. Okay. Oh, you put it up for me again. I should have printed this out because then I would know where I am. So Rasmus said a few things on the panel. Now we're going to deep dive into those things that you mentioned. Yeah. Some of it to you.
Thank you.
See if I can try to make up for the loss of time a little bit.
Don't worry.
Try to go through it fairly quickly. And I think if I remember correctly, I will start with an apologies. There will be no pictures of data centers. So this will be solely about buildings. We will present an investigation done by my colleague Simon and me, mainly focusing on our building in Denmark, but we will also look a little bit about the impact pilot that is also part of the HEATWISE project. So our pilot building, fairly new building, we moved in 10 years ago. So started designing it like 15 years ago, meeting, as we discussed in the panel, almost just the building requirements in Denmark. No additional effort was done. So university building, we have laboratories, we have office for staff, we have lecture rooms, we have student group rooms, and so on. So roughly 150 employees, up to 600 students, and approximately 9,000 square meters. When we turn towards the HVAC systems, we have 9 ventilation units with heat recovery, different types depending on if it's for offices or if it's for that. We have 5 different heating systems. We have decentralized domestic hot water production by heat exchangers, so direct heat exchangers distributed around the building. We have 3 cooling units, and there is a commercial Schneider BMS system operating this. Let's skip to the next one. And
Are you sharing the screen?
I guess so.
On that?
Oh, yeah. You haven't shared the screen.
No.
Now it should be shared. So I will be showing you results from our building, but please keep in mind that no 2 buildings are alike. They can be very modern, they can be fairly old, so they would have very different energy needs, very different insulation levels, efficiency of the HVAC systems, different use profiles, and probably also designed for very different heating systems, both within a region, within a country, but also especially across different countries. So waste heat potential of a building depends on how we connect it. So how much energy can we actually utilize from a data center? It could be in principle other waste heat sources. It actually depends on how we sort of connect it. We heard early this morning about the Luleå district heating system requiring up to 99 degrees of hot water sending out to their customers and so on. In Aalborg, we don't have it as cold as Luleå, so we have around 5 degrees in our heating season, so we don't need that high water temperatures. I think our district heating network only guarantees 60-65 degrees of water temperature. Of course, in wintertime, in peak times, they increase temperature because it's cheaper to increase temperature than to push more water through the system. We can, of course, connect at the main system. So where you sort of have the district heating going into the building, you could also connect your waste heat from the data center. But we could also maybe look at the different categories, ventilation, heating, and so on, try to connect there, see what happens. And we could also attack on the individual systems. So maybe a little bit difficult to see, but the picture to the left, that's a domestic hot water production unit. Even though it's a commercial building, it's the size of a single family house. So it's actually almost to scale on this screen. And to the right, we have a mixing loop for a ventilation system. So we have the heating surface, preheating the air to the desired temperature. In case the heat recovery unit is not efficient enough, then we can add some heat to it. So we can sort of connect different places in the building and at different level of HVAC systems. And that's what is trying to be depicted up here on the right corner. So we have the district heating coming into the building. This is the main meter. Then we can go in and measure just before the mixing loop. If you go back one slide. This is actually the energy meter sitting up here to the right. So we are actually in this building measuring the energy supplied to the heating surface of each ventilation unit measuring the temperature in the supply and return. And that's this T2 point here. But actually what is important is the T1 position, right? So what is actually the temperature required for the heating surface? And the lower we can get, the more heat we can utilize. So what you see on the graph in black is at T3, so the district heating temperature coming in. So you can see that in winter, we actually go up until 85 degrees, but in summer we are around 60, 65 degrees, right? So that was sort of the promised minimum temperature. If we take the red one, that's T2, so just before the mixing loop, more or less the same. There's not that much heat loss in the pipes from where the district heating come into the building to the technical room where we have the heating surface. So more or less the same. But if we attack after the mixing loop, we see that the temperatures is actually much, much lower. So probably around, in average, 30, 35 degrees, going up to 40, 45 degrees. So much lower temperature, much better possibilities of using the waste heat. And here we have tried to, and I hope it's big enough, but all of the graphs up here, except for the black line, is domestic hot water. So the temperatures to the production of domestic hot water. The black line is the district heating. So it's the same on both of the graphs. And what you can see for the domestic hot water is that we are around 50 degrees. So apparently also slightly colder than in Luleå. I think it was 60, 65 degrees, something like that. So we are around 50, 55, so up to maximum 60 degrees. And very narrow temperatures span all around. This area where it's lower, that's actually a fault, probably. It should be up there around the 50, 55 degrees, both for comfort, but also to avoid problems with Legionella. If we then look towards ventilation, you can see it's actually much, much lower. So we start around 20 degrees and end up, depending on which one we take, around 40, 50 degrees. And the 50 degrees is probably something that you can do without. So in the range 30 to 40 degrees, we can really utilize the energy. We also have some numbers from the EMPA pilot that is also part of the HEATWISE project. So this very interesting building that has different sort of labs that you can change up the building envelopes and so on. So it's a very high-tech, very fancy building with a lot of instrumentations. And we have two of the different sort of compartments of the building. We have up here we have the blue for heating, and we have the dark orange for ventilation. And you can see heating temperatures from approximately 30 going up to 34 degrees. For ventilation, 22 to 28 degrees, something like that. So when you do design low energy, very efficient buildings, you can actually go even lower than our 10-year-old, 15-year-old design building, right? So for the other one, it's actually even better, more or less. So all the way down from 18 degrees, we can start utilizing energy, having quite a lot for the ventilation, right? This purple, so going up to maybe 22 degrees. So if we design the buildings correct, size the systems according to the temperature that will be available from waste heat, rather than what comes in from the district heating system, we can actually utilize quite a lot of energy. So trying to sum up, what is actually needed for the HVAC system? Ventilation, normally never above 50. You also get problems with dust starting smelling. So typically around 25 to 35 and rarely above 40. So completely different temperatures than what we see from the district heating suppliers. Floor heating, 25, 35 degrees. Again, quite low. If we have concrete floors, you can go higher, but typically you won't, or you don't need to. Radiators, 40, 65 degrees. And then we have the whole discussion about old buildings, do they need it? Most old buildings has actually been more or less energy renovated. Not many houses have only single pane windows. And there was an investigation done in Denmark that moving or changing windows from single pane windows to a low energy window was actually more or less sufficient to reduce the temperature from district heating from 89 degrees down to 67 degrees, right? So probably most of the buildings, not all, but most of the building are actually ready due to normal upgrading of the building envelope to cope with these lower temperatures. And domestic hot water 45, 65 degrees. So quite soon it will be, at least in Denmark, the domestic hot water that will sort of set the threshold for maximum temperatures. And that constitutes a problem because the district heating companies in Denmark are decoupled from buildings. So they are moving down in water temperature to 60 degrees, 55 degrees, perhaps even. And then the building owners say, well, we can't produce hot water. District heating just is not our problem. It's your building, right? So there's sort of will be some things to thought out. But we are moving, at least in Denmark, very low in the district heating temperatures. So we also try to divide it into the energy use, trying to sort it here. So this is the energy for heating, this is the energy for ventilation, and this is the energy for domestic hot water in our building. So as you can see, domestic hot water that has the high temperature requirements is actually only a small part of the energy. This being a commercial building, heating is quite a lot, but actually ventilation is the biggest one. They are probably equal because there were malfunction in one of the valves in the mixing loop. So some of these very high temperatures in ventilation is due to poor management or faults occurring in buildings, right? So heating, ventilation, more or less equal, and especially ventilation, you can really utilize a low temperature for a large part of the year. And we talked about this also earlier today. What when the data center provides more energy than the building uses? Of course, you could say as a building owner, that's just nice. I can get whatever I need and I don't care about it. But as a data center, you need to get rid of this heat, right? So one thing, of course, is to sell to the district heating. Maybe in Denmark with Studico products and similar products with liquid cooling, we can actually sell directly to the district heating. There is a system up and running in Aalborg where the liquid cooling is actually connected directly to the district heating without any heat pumps. But we also actually looked into several scenarios of utilizing more heat in buildings. I think we had an example in the morning where you use it to melt ice on the pavements. You could put in a storage tank that's done at IMPA. And we could run systems in a way that increases the heating energy need. Right? We also always try to run buildings with a low energy use as possible. But if the energy is there for free or very cheap, we could actually run it less efficient. We could dump in heat through HVAC systems instead of dedicated cooling unit. So we are running the ventilation anyway. So we could put a heating coil in the exhaust and just throw the heat out, utilizing, you could say, the air that we already have to move to reuse or remove heat. There could be some side effects, decreased electricity use. Let's assume we need to take more energy into the building. Then we have more ventilation. We'll use more electricity, but we'll also get a better indoor air quality. We might increase or decrease cooling need and increase and decrease the quality of the indoor environment. Raising temperatures, raising indoor air quality, and so on. So, and if I remember correct, Luleå district heating had sort of a factor of 100 between base load and peak loads. You can see in our building we have something. It almost goes to 0, so it would be infinite. But let's just say it's 2 up to 200. So we have sort of the same in our building, right? A factor of 100 between peak loads and minimum load. We took an example from one ventilation system. So this is the blue one is the heating coil power. So this is what we have used. But if there is a surplus of heat, we need to remove some from the data center. What we can do is we can run the heat recovery less efficient, and then we follow the sort of the orange curve. So we can use more heat just turning down the heat recovery, and that's cost us nothing. We actually save a bit of energy. So there are possibilities of the building to take up more energy than it actually needs without costing us anything. So in conclusion, there is a huge potential to use waste heat from data centers. And we are talking about these smaller data centers that can fit into buildings, so we don't need to move the energy very far, especially if we connect at the individual HVAC systems. So one of the things that we have started teaching our students is trying to have buildings that is prepared for this, maybe have, you could say, 2 or 3 subsystems, pipe systems with different temperature in your buildings, so that you are ready to actually utilize waste heat. And if you want to evaluate the potential of your building, very important that you actually find out what is the temperature of the water going into the different HVAC systems. And remember that the building can act as a heat sink, even if there is no need for heating the building. Good. Thank you.
So do we have any questions? Are there any questions online? Can you see that? So it's interesting, you started the presentation to say we're not going to show any pictures of data centers, but I'm going to show you pictures of a building. But data center is a building, yeah. Well, this is something that we talk about a lot, Mark, isn't it? Yeah. But one of the things that's interesting about this region, we have a large data center here, that in the winter, because it's a direct, well, 2 halls that I know, the 3rd hall, talking about Meta here, is an indirect system, but they use direct air. And in the winter, they're reusing 95% of the heat. So the building is not well insulated. So when we start talking about heat recovery with data centers, we should be insulated. And that's something that's a cost to the data center guys. But it's a conversation piece that I've not really heard anybody talk about. What's your view on that? Yeah.
I think that the sort of, if we take sort of the small part first, should you insulate, right? That depends on if you can reuse the heat for anything. Otherwise, it doesn't make sense. And then I think it also depends on how you actually cool it. So the more you use liquid cooling so that it don't get out into the building, right, would be easier to reuse it, and you would have less waste heat. You will capture more of the heat, so less will go to the building.
Yeah.
So the building will need more heat to have sort of a nice operating temperature, especially in cold climates. So there it would be more efficient. But I think, again, as I said in the panel debate, you need to look at the whole picture. So you should do your LCA, trying to calculate how much energy is invested into the materials to insulate. How much do you gain? What does that cost? Can you utilize it, and so on?
Yeah, this is an optimization problem. Yeah.
But in general, I would say you probably should insulate just a little bit, right? But the amount of it's something that needs to be calculated on a case basis.
From day one, they know they're going to generate a lot of heat, so they say, well, we just need to make the building leak as much heat as possible because we don't really want dealing with heat. But I mean, now this debate about heat recovery, I think we need to have that discussion.
So I think in Aalborg we have a large cement producer called Aalborg Portland, and they produce cement, and you have these large ovens and so on.
Yeah.
So it was sort of just, the oven was just covered with a metal shed. So when they give tours, they tell people, we are walking through it, you're not allowed to stop because your shoes will start melting and so on. And then they ask people to guess, what is the temperature here? And people say, wow, this is probably like someone has 60, 70, 80, 90 degrees. Mm-hmm. So it's like 220. So you put a table and you place your pizza and it's baked.
Yeah.
They reuse the heat from 1 out of 5 or 6 ovens.
Yeah.
And that covers like 30% of the district heating in Aalborg. So there's just huge potential.
Well, actually, I mean, the question is, if I know we're talking about small data centers here, but when you start talking about a large data center campus, like over a gigawatt, what the devil are you going to do with a gigawatt of heat? Yeah. And there's nothing really nearby.
Go back.
Yeah.
The 2 slides. This one, yeah.
Yeah.
So we're using up to 200 kilowatts.
Yeah.
Right? In a 9,000 square meter building. So this 1 megawatt you have.
Yeah. 5 times that. Yeah. So 45,000 square meters. Yeah. Yeah.
So it's just crazy the amount of energy to the computer.
Exactly. Yeah. Are there any questions online from anybody now? Okay, we're good to progress. Thanks a lot, Rasmus. So we're going to move on. Can't remember. Can you put up the yeah, I should. So Mustafa, yes, okay, Mustafa, yeah. Please grab the mic. Here we go. We'll be talking about a self-assessment tool for evaluating efficiency. Yeah. Jumping in.
Hello, everyone. We have 2 successive presentations from DS-TEC on the self-assessment and self-optimization tools. The self-assessment and self-optimization words are keywords indicated in the project proposal that we need to address during the HEATWISE project. In work package 8, we are continuously developing and updating the self-assessment tool. Mustafa will introduce the self-assessment tool, which has been developed for the evaluation of the efficiency of the data center based on KPIs. We will have around 16 KPIs. We will demonstrate the result. And after that, Başak will introduce self-optimization tool, which is aimed to optimize the cooling system deployed in RISE and EMPA pilots. Therefore, we will be very happy to get your feedbacks and your suggestions and your questions. Good
afternoon, everyone. Today I will present self-assessment tool developed within the HEATWISE project. Why does data center efficiency matter? Data centers account for a rapidly growing and it consumes around 4% of electricity use in the world. And also rising pressure on energy efficiency and sustainability is driving data centers to adopt more structured and measurable assessment practices. Since 2024, Energy Efficiency Directive mandates reporting and continuous performance improvement. Why it matters? Energy Efficiency Directive wants report mandatory KPIs such as PUE, COP, water usage effectiveness, renewable energy factor, primary energy savings, and data centers must report regularly. Reporting process is manual, fragmented, and time-consuming in today. Only according to European Data Center Association first report, only 770 data centers participated in first reporting. The major challenges are data access, compliance, and also time-consuming. Also, our solution aimed at automated ED reporting platform. Our platform features are fully KPI compliant, auditor-ready documentation, no manual data handling, test reliable and user-friendly, and also fully aligned with the European Union targets. So there is a structural gap between regulatory requirements and daily operations. Bridging this gap is the main aim to our work. I want to talking about the self-assessment tool features. The self-assessment tool is a flexible KPI-driven assessment platform. And also it operates a web-based service that can integrate directly DCIM tools, SNMP, or analyze data sets manually uploaded by the user. The tool automatically generates comprehensive EED aligned or also ASHRAE aligned performance reports for the data center. We have 4 main modules in the self-assessment tool. The first of is automated data capture from sensors and monitoring system module. The second one is a real-time KPI calculation module. Also, we have interactive dashboard module, and the last part of our tool is the automated PDF report for management and regulators. That's a big question for the data center environment, I think. Which of the following indicators are actively measured based on actual data? According to European Data Center Association surveys, as you know, PV is most famous KPI in data center environment, but we have very important challenge in this survey's conclusion. ERF is very critical for us. We have 16 KPIs in self-assessment tool. Is the first part is EED aligned regulatory KPIs, PV, ERF, REF, such as. Second part is we offer some thermal KPIs, some additional KPIs and optional KPIs in HEATWISE project. Our tool actually validates data, harmonizes metrics, standards that it provides standards that methodology, and also it produces regulatory read output. But this part is very important, I think. The broader the data label coverage, the more comprehensive and detailed KPI assessment becomes. Actually, more data, more insights, and better decisions. Features of the self-assessment tool. We have 3 main features in our tool. The first one is data module, I think. We can connect data management system or monitoring system, and also we can upload the data from an external source in our tool. Also, we have 5 HEATWISE pilots, and also we will implement our solution to 5 external pilots. And we have a reporting module, the last part. And also we published our tool, first version of our tool in Energy Informatics journal. Latest version of the set includes real-time data integration, comprehensive KPI analytics, advanced data processing engine, interactive operational dashboard, multi-data center supports, automated reporting and modular and extensible architecture. For example, literature or policymakers or regulations suggest new KPIs. We can easily integrate our tool. The self-assessment report layout includes data center overview. For example, data center name, cooling strategy, logging intervals, also water and air inlet outlet temperatures, total server power, and geometrical information about the pilots. And KPI summary and assessments. Also, it provides KPIs graphic and also inlet temperature, CPU temperature, and power heat maps. Self-assessment tool, market value of the self-assessment tool. We aim automated and consistent reporting, and it detect hotspots and inefficiencies. Also, it compare across sites. It can make benchmarking studies. Also, it saves the time, supports cost reduction, supports compliance, and strengthens brand. Commercialization activities are being developed jointly with H1S, and SAT implementation has already started at H1 systems as an first external pilot. Yeah, my last words are self-assessment tool provides data integration, standardization, reporting, traceability, scalability, and reproducibility with low error risk. Thank you.
Thanks, Mustafa. Do we have any questions for Mustafa? Yeah. So yeah, self-assessment. So that gets us to one part of the process. Yes, the reporting. But can it? Do you envisage that your approach will help improve the system? You know, obviously you're going to report metrics, and the metrics. If you get a green tick and say, yeah, I'm compliant. But what about understanding whether you can go further? Is that something that you're going to consider later on?
Yeah, we have already.
Yeah. The boss wants to be.
Sorry. I just want to share. It's a good question because in the self-assessment report, a table is generated.
Yeah.
And based on the calculated KPIs, some comments will be provided as the efficiency can be improved or not. And at the final report, some recommendations will be provided in the document. How can the efficiency of the data center be improved?
Okay.
In order to address return temperature index, return cooling index, because we have classified the KPIs as energy, thermal, and wasted KPIs.
Yeah.
We will suggest some recommendations and retrofitting alternatives at the end of the day.
Okay. Thanks. Yeah. And it seems like that would be very useful.
Yeah.
I mean, the whole idea of these metrics was to see how you improve yourself, how you could make improvements on your systems. Yeah. Mark,
Is it worth considering? Is it worth considering integrating with the EN 5600 5-1, the surety model?
Oh, I haven't.
Okay, because I think increasingly we're probably going to, we'll have a conversation afterwards, but it's something I think the Commission are probably going to be using more going forward. So there's not much overlap between what you're doing and what it does, but I think together it could be a good combination.
Yeah, it can be done, I think.
Oh, sure.
We have integrated the self-assessment tool with the data management software developed by RISE team in package 6. Therefore, we can retrieve the data simultaneously from the data management system. Maybe we can integrate the self-assessment tool with the data.
Sorry, trust service.
Yeah,
the data service.
Is it?
Yeah, country much surprised.
You personally validated, John.
Heavily validated, yeah. Thanks, thanks, Mustafa. Yeah, we're going to move on. Yeah, thanks for that. No questions online, David, is there? No. No, okay, you're keeping an eye on that for us, yeah. So Aslak, you're going to talk about thermal prediction and optimization models.
Yeah, mostly on thermal prediction surrogate.
Oh, okay, on the surrogate, okay. Okay, take it away, yeah.
So I'm going to be the thermal prediction surrogate in order to maximize the waste heat in a kind of way. So data centers currently consume about 1.5% of global electricity consumption. Is about 450 terawatt hour. And with demand growing to the growing due to the accelerated computing and AI usage, and its global statistics for the EU data center consumption was estimated at 70 terawatt hour in 2024, but expected to rise 150 terawatt hour by 2030. So you can skip that. Okay. Yeah. So there is actually because of the energy demand. The heat reuse in data centers can be critical in kind of way. The waste heat typically ranges between 25 and 30 Celsius air cooled, like for air cooled data centers, but this is the average temperature statistics. It can change the type. It can change depending on the type of the heating that you are using currently for heating waste in the data center. But there is a huge demanding, not huge, but significant demand for practical reuse for the waste heat. And the predetermined supply heat for the data center or a building, depending on the climatal changes and the cooling system architecture. And key barriers remain distance to networks, infrastructure costs, economic feasibility, and temperature mismatch mostly. And there was a survey plot from the European Colocation and Hyperscale survey from 2024. The percentage was 46 for the question of what are the main barriers to the export of heat. It was saying that quality mismatch of waste heat supply and demand, and it's decreased to the 28% by 2025, and it is promising actually, because there are some ways taken to shrink this gap of minutes, I guess. So why traditional cooling limits heat recovery potential? Because of low quality heat output, mostly for air-cooled type systems, and it requires air-to-water or air-to-air transfer layer. Actually, not air-to-air, but air-to-water transfer layer. For example, extra coils, pumps, and variable losses, of course. It is limited also monitoring for heat reuse optimization, and they are difficult in integration with local energy systems. Why data-driven optimization is needed? Data centers already operate close to high efficiency, and yet significant energy savings remain possible. And cooling systems involve complex and nonlinear interactions between low temperature and flow, and kind of it should be. Operators typically rely on static set points and conservative settings, but it should be in some kind of way, maybe because it's tradition that, not tradition, I don't want to misinterpret the things. Let's skip. Okay. As actually self-optimization tool will have two module. We said from the data pipeline perspective, we will be using the live data in the future, but now I actually we are right now manually give the input to the system, but with the more data and with the retraining module, we can decide whether I will be put my links into a solid base within the next slides, I guess. Okay, so thermal prediction model uses machine learning to learn the thermal behavior of the HRE cooling system from the operational data, but this operational data, of course, should be meaningful to be to predict the targets to be optimized. I mean, meaningful in a way for model should learn the relationship between the input parameters without overfitting, because if you put too much data to as an input signal to your thermal prediction surrogate, then it will overfit. But next slide. But thanks to XGBoost, actually, it's easy not to overfit using XGBoost, because you can set hyperparameters with high number of estimators, but you can set the learning rate small, and it will eventually stop when it has when it will reach the best like it has early stopping condition. So temporal lag features has used for thermal inertia learning, and penalty functions, penalty losses has been in XGBoost algorithm. There are penalty functions for prevent the overfitting. So L2 is activated, and also it can be fully integrated with live data pipelines. Yeah. This is a representative schematic only. In the model, when we have the control volume of the HRU, so there will be a T1 from water temperature coming from the branch, but T1 and so as a supply T5, HRU supply temperature to the dry cooler, and in the HRU, so we want to maximize. If you want to maximize the waste heat captured by the coolant loop side, so we have to make a meaningful correlation between the parameters that eventually affect the outlet temperature from the HRU exchanger side. So temporal features are really important, because the base differentials are a bit the trend change, like the change in the parameters within given the specific lag arrays. Like if you, for example, I downloaded data with 5 minutes resolution, and I select the leg 1, 2, 6, 10, and 12, but it was the first shot. It means that I want to look 5 minutes ago for what this we did. I mean, how these parameters changed, and wanted to look 10 minutes ago. So it's like it is scaling with the resolution of data to be able to capture the thermal energy. For example, can you skip? So if I'm not wrong, there was an interval where the IT loads decreased, like moderate level, total IT loads decreased, and the valve opening ratio, the mass flow rates, I mean, decreased there. So the liquid temperature at the outlets of the heat exchanger was decreased at the first, but then increased slowly. So where it settles, I took it as a total response of the system to be able to define the thermal energy at that point. So when I will change the word, I mean, for the specific given PIT, what will be the system response? So I try to capture that. At the end, for the train data and this taste data, you can see it fits within the outlet water temp, the prediction and measured fits better. That's interval. But for this, when the measured but when this sudden change in the valve of throttling, I mean, because the model didn't learn it very well, it means that I should do leg tuning, like I need to do grid searching for the best leg candidate. So the one way to do that is leg tuning as a grid search. Another thing is more data interval ingestion, like this transient interval for the system to be learned. And it's really fast in a kind of way because of the architecture of the XGBoost model. Yes. This is so the kind of prediction error and frequency histogram for the TPM for the specific period of the test interval. I say something. Yes. Yes, actually, this effect can be seen in here better because it's a large spike residual remaining, and we will be training the model with more this kind of transient interval and improve the model with lag tuning. This is the different custom train interval. And also R squared is kind of acceptable for the previous custom training report period. It was 0.81, but because of the this transient sudden abrupt change in the bore and model didn't see it. It's kind of slow and it is decreased like that to the 0.74. So yeah, it is acceptable right now, but for the eventual result, it should be improved. What we are doing for the self-optimization tool in total. So we maintain close collaboration with the EMPA and RISE pilot sites and continuously monitor the cooling system behavior and what are the limitations for the supply temperature, heat demands, or the IT capacity. And we also update and retrain the thermal prediction model with the more transient data sets. And it is the schematic of, the timeline, not timeline.
Roadmap.
Yeah, roadmap. For the development for self-optimization tool. So optimization is pending right now, and when we finally finalize the prediction model with the living data from the repository with the live integration with the live pipeline. So we will be able to optimize the system, not optimize the system, not we will be able to optimize the system, but we can eventually. So for the future studies for SOT, we will develop pilot-specific waste heat optimization models using the collected operational test data sets. And the SOT can be integrated into the pilot's holistic control framework as a modular component, enabling automatic well set provision via Modbus. We aim to evaluate the reusable waste heat achieved by the SOT through quantitative analysis of relevant KPIs. We aim to identify potential energy savings and operational improvements enabled by data-driven optimization strategies. And the results will support the validation of SOT methodology across different pilot infrastructures with direct chip critical pilot sites.
Thank you. We do have time for questions. Yeah. Any questions for the So maybe I can ask a question. So the two sites, EMPA and RISE, are obviously using the same technology, yeah, in terms of the direct-to-chip system.
Yes, yeah, we aim to use the same structure.
Okay, yeah. So is the model purely data-driven, or do you inject some physics into that?
Actually, it is data-driven, but the philosophy behind the, for example, putting these base features comes from semi-thermodynamical relations.
Okay, so you are using some thermodynamic relations as well, yeah.
Yeah.
Okay, yeah, that's good, yeah, that's usually helpful, yeah. Any other questions from anybody?
Can I make a comment?
Oh, yeah.
Yeah.
Sure.
It's coming. So it is just to encourage us to pursue what is being done here. It is just, I was writing another proposal last week, and I had to deal with AI implementations in fermentation processes. Oh my God, like there are a lot, it sounds dangerous, but it actually, like the purpose is so noble after all. You can make beer with this, better beer. So
see what happens.
It's, yeah, my point is I'm more and more encouraged with these database models. Because what we do is basically easy to solve with the right data sets, with the right amount of data. I would say that most of the things we do, if we focus on the right angle, from the right angle, like if the HRU in this case, like or cooling distribution unit, what we want to focus, basically the data streams, like the data is so similar. So it is basically easily scalable if we build a data-based model, try to reduce the size of the model, limit the physical models on the system. Because in the fermentation, there was genome models, like trying to understand like which microbe we use, what is the outcome, what the beer would taste. It is not only beer. It's bioplastic beer and everything. I know it's complicated, but my final takeaway after writing this proposal, we are way in a better position than many processing industries to actually come up with a lightweight, easy to use solutions to actually improve the operations in the data centers. Just we need to look at the right place. This is, I think, what we are trying to do in HEATWISE. Obviously, it is a process. We are still collecting the data. We are still improving the system. We still have time until the end of the project, but I'm a bit encouraged. We are a bit lucky. This black box system can help. So, okay, just one feedback.
Thank you. Anyway, well, I think, okay, thanks a lot, Professor. Yeah, thank you for that. So, getting a little bit more optimistic with data, I think. Are we going to blow us away with digital twins for holistic data center management? You're going to use your computer?
I may, but you may also want to save time. So I'll just run the slides and then you can feel the room a bit.
If you want to do a demonstration, yeah.
I have prepared.
Okay.
Things.
Okay. Yeah. But
you want to?
Yeah. But then the teams will drop. Yeah, that's the problem. Yeah. So our online people will not be able to see what. Unless are you going to connect? Yeah, join the Teams call. And yeah.
So after the presentation, we can unplug it.
Yeah. Okay. So show the presentation first, and then you connect. Yeah.
This is connected?
Yes, that works. Yeah.
So it's been quite an interesting day with many discussions and perhaps some arguments, some challenges, and where things are heading, what we can do. Some of you have seen the RISE pilot. That's going to be a highlight today as well. Anyway, my name is Henrik Wahlström. I'm a researcher in sustainable data center technologies at RISE in Luleå, also a PhD student at the university here in Luleå. So for the next slide, we have this thing, the challenge of digital twins. There are, according to standards, when we look into digital twins, there are many kinds of interpretations. So I chose a perspective where we have three levels. We have monitoring, gathering the data, we have adjustment, and we have automation. There is also the level of simulation in conjunction with running something. So what's approached here is these problems. So excess heat, underutilized, workload scheduling is usually like siloed, meaning Kubernetes schedules are not optimized for heat reuse. This is the next challenge to sort of approach as well, because if we are to offer infrastructure services to software companies running live software, real workloads for AI or whatnot on edge nodes, we have to be able to provide the whole package with heat recovery and the scheduling. So there are a few existing solutions. As I mentioned, we are quite early in many of these processes and innovative. So holistic is a word from a different project where we approach the embodiment of being able to also demonstrate this by the end of the project full on. So we see the pilot rack at RISE with the heat recovery solution at the bottom. We see some blade servers hardware, and we see some of the in-house chip load emulators that RISE offers to test the cooling equipment. So for the next slide, we have this challenge once again. So digital twins. We have buildings with all work shown us earlier today that we can actually make good use of lower temperatures as well. We talked about district heating. So building control, we have internal data sources, we have electricity prices. We need to report to authorities about how well we're using our data center and so on. We have the IT rack with all the data that implies. We need to, maybe we want some hot water for our hot water tap, but then we would have to put like fictive workflows on the rack, and we would have to know how much workload to put to get back certain amounts of heat. So for the next slide, this is the implemented cooling solution by the team at RISE. It's quite something in terms of testing out the concepts. So we're able to gather a lot of insights for how to deploy the systems, just like EMPA. Difference is we have this in homogeneous architecture, so the TTVs and the blade servers. So this is located in the RISE warehouse, where we also have this building district heating system connected and fetching live data from that one. And the next slide kind of sews this together. So we're looking into the architecture of the digital twin. We have external data, we have the digital twin with its like the entities and all the information flows and all these sub-softwares. So because I'm not a weather expert, so maybe I can pay some weather expert somewhere to provide me with high quality data. We use that in the framework, similar with the building stuff. We have a building modeling expert providing some model, we can pay that. The WHUR engine, so the sort of intelligence, the workload to heat or coordination inside of the data center and the physical solution and whatnot. So we have Bashak here providing an opening into this kind of coordination for the heat on the level of the heat recovery solution. Then there are a few other softwares included here. So we have the telemetry bridge to be able to talk and give settings. So for the EU project side, we have many different places on the map to coordinate and send information safely and so on. So MQTT solves that problem together with the systems. We have the self-assessment, same concept. We are able to get the service for doing that, which means it's also a scalable concept. If we decide to deploy many kind of solutions like so. And then optimization and how the operator is supposed to work with this is another thing. So from like the bottom up to have the data center and the thermal management, this is quite the challenge. So next slide shows us just a hint of, okay, we connect to the Swedish Weather Institute to get the forecast a few days ahead. Just for fun, I've added a few different locations, so we're just able to like press a button. We fetch different kind of weather for different periods, wind speed and solar availability and so on. Building model right now is very simple building model included for the demonstration purpose, where we estimate the amount of heat for the RISE building. So next slide. We have to then figure out how to combine the needs of the building with what the data center can provide. And this is a multitude of complexity. So we talk about the primary side of the district heating, the secondary side, what heat exchangers, the hot water taps. If we want to use air for heating, different kinds of recirculation for air sides. So many combinations. Something to take away from today is like we have this supply temperature. So the data center will be able to supply on the liquid and the air sides on certain temperatures. Then the question is, what can the building receive and what buffer do we have? So if we theoretically install some heat exchangers of sorts, how would those heat exchangers fit into this example? So next slide. Another thing to take into account is the execution of the hardware and software as well. So right now there is an implementation where we send set points through various interfaces to the hardware. We apply load to get to know the system. We do this by either doing it manually. We have like some tabular idea where we load some sequence of tests that we want to do. Another idea is to do some policy-based things. So the policy can be we reuse heat for the hot water tap. We have a theoretical test maybe where we reuse the heat for the hot water in the building, for instance. And then there is also this data-driven path where different models can act as solution providers for the set points and the loads and so on. I mentioned earlier Kubernetes, and this is like a completely different challenge. So small thing, because we all know machine learning solutions are complex and takes lots of time, lots of data. There is many different ways of implementation. Part of me believes that simple physical models are more valuable than we give it credit for. So I threw together a Modelica style-based model for the cooling system that we have at RISE. It's not so calibrated. It's crude parameters from the internet. However, we are able to see transient developments and the realistic outputs for various server loads and so on. And in the digital twin framework, so if we take the next slide, we would be able to estimate different outputs. So we have a live pipeline and we have a simulated pipeline. So if I have a rack somewhere with softwares running and it has to be reliable, I would have the live pipeline running all the time, regardless of if I do theoretical experiments. So for the live pipeline, we fetch the weather, we model the building needs, we decide what do we want to do with this information, maybe electricity price, maybe whatever. We send the set points, it could be workloads, and the workloads could come from some customer somewhere. We have the set points for the cooling system, and then the hardware responds with all this. We gather the information into databases, and then we have a look at what kind of results do we get. To simulate in parallel would require lots of these tests. So, however, once we have this, we would be able to show it side by side. And then also do the self-assessment to see and optimize against different KPIs and show it in some sort of analytics interface. So for the next slide, in parallel in this framework, we have a simulation pipeline. So what we do here is we have the actual digital twin. So if we want to test the hypothesis on some strategy for this intelligence layer, like the WHUR, we would implement it, we would press play, and the pipeline would fetch the results from the various solution providers. And then we would see the simulations, the results, and we could reiterate. So this is sort of how I would love to have a digital twin run, and to be able to work with it and give it to someone who wants to run their data center. So next slide then. So I've been talking about some softwares like modeling solutions, pipelines, system architecture, and all of this is then put together in a way of working with it. So we have like the weather model is up and running now, building model, cooling system, simulation, like this physical model, WHUR model. It's offline because we're running manual set points at the moment. So at some point we will be able to plug in different solutions and compare them in terms of KPIs and whatnot. Workload orchestration. We have an external service to be able to put the load on the servers. This could also be a different kind of workload orchestration. It could be some Kubernetes Slurm solution, I don't know. Optimization service, assessment service, database, meaning the digital twin has access to the database where we choose to store the physical outputs, results. Broker I mentioned. There's a link to just some to the Grafana page to be able to reliably see this in a prepared environment. And then for those of you who have some interest in British humor, we have I call them Jeeves and Wooster. So Wooster is this very rich, arrogant kind of person, a bit clumsy, but does. But it's there, right? So, but Jeeves is this AI assistant. So they are also plugged in right now, and it's a recent development, so it's a very early stage. Conceptually, it works. So, yeah, we can pick the next slide. Is the run. Yes, please. So in terms of pipeline, we have the process, we have the weather building, we have how to plan and implement things, some monitoring, and then what we report to EU or whatnot. So, and then we select, do we want to run a live on the real hardware or simulation? And now it's selected live here. So we have a weather running continuously. We have the building in place, like the RISE type of building, and the manual strategy. So if we would run a simulation, you would have the same thing, but we would select, like, do we want to run the weather or like some file or something. Then this screenshot just shows like the strategies, like manual control, tabular, policy-based, or data-driven. So far we have set a baseline for what's possible to implement. So it could open a path for many researchers to work and compare and implement results. So next slide. I was hoping to do a summary and live demo. But we have something that's tangent on the line of a holistic digital twin, some beginning part of something, and then a way of coordinating things on the hardware. And we can also validate it. So it's up and connected with the RISE pilot. And the next slide is the next to last one, where I just want to show this picture of me misspelling something. So, and the HEATWISE digital twin, is it running? And then what this LLM does, it thinks for quite some time here, 17 seconds. It gets the results from the tool call to the digital twin frontend. And the frontend is connected to all these APIs. So when we deploy it, there are certain methods for how to connect APIs with LLMs. And these standards came out last year. So now this was an opportunity to implement it, to be able to talk to the hardware, sort of to set workloads, to get workloads, to set system parameters. So it just tells us, okay, the digital twin is operational. Here's the state of the things. So it's live, like the UI is selected in the live mode. The services are healthy, and no simulation running. The RISE building model, the manual mode with building as the king. There's also this like software king, building king kind of idea. So weather source is the live API, MQTT is live. And then workloads and KPIs, this was when nothing was running. So it's kind of prepared. So this is what we're working on at the moment, developing. There's one more slide, I think. So it's just kind of showing that this is what we do. Thank you.
You want to show it, do a demonstration?
You want to see it?
I don't know, that's what's the appetite to see it?
I think we are running out of.
No, do we have time? No.
Don't say yes. Do we have? No.
Oh, okay, we don't have time. But anyway, you've given us an idea there. Yeah. So any questions for Henrik? Yeah. Henrik, yeah.
Yeah.
You want to speak just for a moment?
Thank you. The idea of integration, self-assessment and self-optimization tools with the digital twins is great, I think. Now I can say that the recent version of self-assessment tool is now accessible. We deployed the tool in a private server, and we can now integrate with the digital twin because the KPIs are calculated by the self-assessment tool, and the calculated KPIs can be shared with other tools under the umbrella of digital twin, which is a great idea in my opinion. We are at the very beginning of development of self-optimization tool, as presented by Bashar. Once the self-optimization tool is ready, we will be very happy to integrate with the digital twin. Yeah.
Okay.
Just a feedback.
That's just a feedback. Yeah. Thank you very much.
Thank you.
Sounds interesting. Yeah. So, I think one thing I wanted to ask is there anything to do with obviously you've got weather prediction, but actual IT demand prediction? How do you bring that into the equation? Because that's it can be a little bit erratic or unpredictable, perhaps.
So I would interpret the question as IT demand from customers deploying software on the
Exactly. Yeah. Yeah.
And predicting this is quite a challenge. I know there are some papers in circulation and measurements and typical AI profiles. So this could be an interesting next step to run typical workloads to get a feel for the response of the systems and possibly a path for research as well.
Yeah, I think that's where we can build in quite a lot of optimization. You know, when we start understanding the demand for this, the demand for the digital services, and then linking everything together. That's what the future might look like. Yeah, and Mark might be a bit skeptical on that one, yeah. Particularly with these guys in the industry and everything. What do you think, Mark?
I think it's difficult to predict. Yeah, I think it's difficult to predict demand because that's going to be, you know, those workload. Oh, sorry, we have now humans. Yeah, but they're going to submit effectively batches. So I think it's very, very difficult to predict what's going to come down. I think what we do need to do is react to those workloads as they ramp up very quickly. I think that's a different thing. Maybe that's what you're talking about. And I don't think we can predict workloads necessarily coming because, again, that's going to be human defined. It'd be nice if it told us, but again, it's back to communication.
Yeah, it's a good point.
Do we need to predict if how flexible is our system and how quickly can follow the changes? Yeah, that's my question. Like with the cooling, usually is the problem. That with the air-cooled power, yeah, that is the ramp up. But with our hybrid cooling, I think that this is what we are also investigating here, the digital twin. How can be operated? What is the reaction time? There is any delay that do we have time that until we reach the appropriate level of cooling or cold air? So we are probably not yet there now.
So I'm not sure if this is a question, but I will just speculate a bit. So in terms of reaction times of the system, technically, there is no obvious. I might not be able to see the same technical challenge due to the solution provider implementation of the system. So we have a fixed boiling point, and if there is load to the servers, I believe there would always be a supply of coolant anyway, to some degree. So I might be misunderstanding something.
Yeah, maybe a clarification on my side. So at the moment, what's actually happening in high density deployments is that there's a concern that what liquids you're using, we can effectively boil. I know we're talking about boiling and going to the two-phase and going to sort of the gaseous phase. If that happens to a significant extent, there's a really strong chance that chips are going to overheat. So what's actually happening in practice, rather than us punctuating the cooling flow, it's eventually working, according to the demand. What's actually happening in practice is they're just running the pipes out all the time. So actually, the energy requirement goes up. It's actually being run in a very, very efficient manner because of the concern about not cooling. So so the reaction time actually isn't. Then we have to have confidence that these systems can react very, very quickly. We're talking about megawatts of load here. We're not talking about watts or kilowatts. We're talking about megawatts, and that's the challenge.
So it's Anna.
No, I'm not sure. After this is I just would build up on that what Henrik said. So once the load rises to the chip, right? So there is a fixed boiling temperature. So that is managing the load of the chip itself, I think. And then there is the air component, which is cooling the auxiliary chips, like the memory, or some other stuff. In our case, there is no AC, in our test. So practically, the heat what is generated by the memory or motherboard, whatever, that is actually also getting into the liquid system, which is going to the CPU. So probably there is no delay in that. I don't know. Probably self-optimization tool is going to give the answer to this question. Whether we have to forecast and we have to prepare the cooling system for that.
It's the liquid flow rate. It's the flow rate.
Yeah, the flow rate is, and I think the pressure is controlled right in our system. So we don't have to pre-cool, if I understand the last system, like in case of air, but that is not that much.
So I'm understanding a little more from your comments now. So it's a pool-based boiling system. It means there is always at least a certain amount of fluid available for a buffer time. Then if this buffer time is enough to provide for the high voltage, like on and off kind of workload, I'm not able to answer the question at the moment intuitively. Why not? This is why the question wasn't, the answer wasn't obvious earlier. So, yeah.
Yeah, I think we're talking about maybe two different scales of system. On the one hand, you've got a small building system, and what you were talking about is that they're in a direct-to-chip system, which is single phase, that is running AI workloads. The swing is so dramatic that they run the cooling system flat out anyway. Yeah. So you can. There's no room for optimization. Well, there is room for optimization, but everything's happening so fast. Yeah. Okay. Well, and we got a good debate going.
You're talking about the sizes, and I think I missed mentioning it. That what the size that we are talking about. So we are thinking of a modular system, and in a proposal we put that we would like to reach an energy density of 100 kilowatt per rep. Now we are experimenting with 10 kilowatt, 16 kilowatt per rep, right? And we would like to do conclusions and then we can reach that density, and that is when things become interesting. It's a small scale.
Yeah. Well, thanks. I mean, Sharp, it's going to shoot me, Matt.
No.
What's going on?
I'm about to forget the question of yours. That's why I was just trying not to. Just we should remember something. This is a research and innovation action. So the results they are expected at TRL 5 level.
Yeah.
So there will be follow-up projects where we're going to be working on up to TRL 7 level. Actually, this event we actually had the chance to start discussing like future TRL 5, TRL 6 options, like what needs to be done. But about your question, John, now we are not in a rush to answer how we can predict the workload. We are just trying to validate our solutions to how we can improve like holistic data center management that I inspired by your previous work from the beginning, where we want to actually control the workload and the cooling element in this case. In this project, there is no power, but the system that we are working, it's easily, it can be scaled up to power systems and so on. This is the first thing. And the second thing, I think it is fair to say, in a real data center, in front of Mark and John, it's difficult to explain these things, but yeah, I will try. Like everything, like the control systems are working on silos, right? Like on the IT there, we have a silo giving board management systems and so on. This is what we discussed, like all the valuable data is going to trash, usually we are not using it. And on the cooling side, there is another silo working with usually not so smart, predefined control algorithms and so on. And on the power systems, it is the same. And if we are discussing about connecting them to a smart grid, again, another silo, which is even outside of our comfort zone. I would say that I was really happy. I think as a team, we had a eureka moment when we started realizing that, we have a way to communicate with the buildings, like the WHR module that Henrik just introduced. It's a good step to automatically discuss with the building, what do you need? And let me see if I can answer your need or not. Like this is the first step. And while doing that, we are trying to also combine the silos. The value of a database management system, I think, is there. Henrik explained it brilliantly. Like in the technology we have, it also already has some advantages. But with what we develop, with the real-time data processing power that we have, we would be actually checking the active components in a way that we wouldn't be. We would make sure that if you consider like a beer colony, we wouldn't be only checking how much honey that we can have. We would be also checking the health status of the bees inside, and we try to maximize the sustainability in this ecosystem. I mean, these are good plans, difficult to make. All we are trying to do, the optimization model that we introduce, it's not going to be that costly and really heavy that nobody wants to adapt it. At the end of the day, I think the main idea should be whatever we are proposing, it should be real life applicable at the end, and we do our best to reach there.
Thank you.
Yeah.
You're winding up the meeting then by what you just said. So on that note, I have a few minutes to do the closing remarks. I think the first thing I wanted to say is to thank all the speakers, contributions. Let's do that in the usual way, and clap our hands for all the speakers and all the contributions, please. And obviously, thank you as the audience, because you've participated and I'm sorry about my timekeeping. But I guess it's kind of which time zone you're in, and probably on time. But just a few points of remark. I think it's interesting what Shafar just said. I mean, the problem sometimes with EU projects is that there's a lot of great technologies that come out, but it's actually getting it into the mainstream, which is the main problem. And I think the more we engage with the industry and I think and do these kind of events, try and get people to listen up to what we're saying, the more likely it is that people are going to catch on to these things. And at the end of the day, with this industry growing as much as it is, I don't know whether it's 1.5%, 4% or 7%. I don't think anybody really knows how much energy this industry is really consuming. I mean, it's always a good starting point to say that it is consuming a lot, And as an engineer, you should never really use the word big, small, long. You should have to give it some quantity, but I think with energy you can't. And to recover that energy is obviously a very commendable thing that we need to do. And I think in Europe, that is where I think we could lead the way. And perhaps we are leading the way because there are some good examples of heat recovery from data centers. But I think the only thing I would like to say is that there's I think the last few talks, there's some elements of some clever integration, I think, and building on past projects like you mentioned, Sharpe, which I think is great to see. And I guess what's going to happen next is we're going to go and see is that going to happen? Is that the idea?
Yes, like the ones who would like to see the lab before it is too late and it's closed, we can actually go to that direction and you will be able to see the lab.
Are we taking the people online as well to the lab now?
Unfortunately, it's not going to be possible. So it would be on just for the people here. Yeah.
But I guess so the last thing to say is to thank those online that have assisted and listened in.
Yes.
Online. Any of the questions? We have a couple of good questions from online.
A couple of good questions. I think because of the time limitations, we had to move on right now. But we agreed with the team. We will check the questions and we will be able to answer them online. So a bit more patience about this, I would ask.
Okay. So it's over from me, and thanks to Sharpe for allowing me to do this. He didn't know what he was getting, what I didn't know what I was getting myself into a meeting. But anyway, there you go. So thanks a lot. Yeah, thanks to you.
Let me also then thank to all the consortium and all these teams. I would just say something like, when you are doing something that brave, we are basically getting out of our comfort zone of the data centers a lot. It is risky, and it is, what is even more difficult, it is to present it in front of Mark and John. Basically, it can crash the ideas in a really, really difficult way. So I think the team and all the consortium deserves a great applause before the data center visit.
Yeah, well done, guys. So we say goodbye to people online.
Yes.
Coffee break. Or
coffee will be there. I don't know if we have coffee left, but it will be there in the ICE data center at the entrance if they want.
Okay.
So, I mean, whoever wants to visit the data center, they can join us. So we can just walk to the data center, which is not so far. One more thing, I see that you have the bags here. I think it is quite safe to leave it here, but maybe